Women in Computer Vision workshop. This year, we are organizing the 11th Women in Computer Vision workshop. And we are really happy to see all of you here and all of you on live stream. So I am Ziqi Huang. I'm one of the organizers of the workshop this year, and I'm currently a PhD student at NM Lab at NTU. So I will just take the first 10 minutes to introduce what is the WSCV workshop, why we have this workshop, and also our schedule today. So why do we have our Women in Computer Vision workshop? Well, the computer vision community is getting bigger and bigger, but when you look at the CVPR conference hall, or when you look at your lab, your company, where are the women? In this figure, we see that at undergraduate level, there are only 33% of female students studying in science and engineering. And the percentage of women actually keeps dropping when it goes to higher levels of education, such as postgrad and lecturers and professors. These stats might vary based on regions and cultures, but overall, I believe we all see that the percentage of female faculty and researchers are relatively low. So there are two aspects towards this phenomenon. First, to start with, sorry, I just start the screen share. Just give me 1 second. It's working now. Okay, great. Yeah, so we are talking about the percentage of female researchers are relatively low, and there are two aspects towards this. So first, girls are less likely to study STEM subjects. Luckily, nowadays, more and more women are getting education, and we see that at undergraduate level, when we consider all different subjects, there are actually half of female students among all the population. However, we see that for science and engineering majors, especially computer science, the percentage of female students are very low. So, yeah, on top of the very low percentage, we also have this leaky pipeline problem. That is, the percentage of female actually keeps dropping when it goes to higher level of educations and later stages of the career. So in academia, for example, there are some key transition points. For example, receiving a PhD degree, doing postdoc, or obtaining a tenure track position, being promoted to full professor, and even institute director and research leaders. And at each of the transition points, the percentage of females decreases drastically due to different kind of reasons. And we really hope to see increasing gender diversity in this field, because the low percentages can sometimes create isolation and lead to lack of inclusion around workplaces. A greater gender diversity brings more diverse perspectives and can provide unique insights into research problems. So we hope to encourage and support women in computer vision, and our workshop is part of the efforts. So there are three main goals of our workshop. First, we want to raise visibility of female researchers, and to achieve that, we have high-quality research talks by female researchers or professors who are role models in this field. And the second goal is to provide opportunities for female researchers, especially junior researchers and PhD students, to present their work via poster sessions. Some of us might not actually have the chance to be at CVPR, either financially or we don't have that supportive environment to have our work seen. So we try to get over the economical or social barriers by providing travel awards and hosting the poster sessions. And the third goal is to discuss the inclusion and diversity topics in a very open and friendly environment with both female and male researchers. For the panel session and the mentoring dinner, we invite panelists who are strong role models in this field. And some of them are even the previous bachelor's WSCV organizers who have later become professors or lead researchers in their lab. And we are really glad to see them back this year to share their experiences. So here are some stats about our workshop. This year, we received 68 submissions in total, and 61 of them went into the review process. The program committee decided on recommended 6 orals and 34 posters. So congratulations to all the authors. And this year, as we the organizers, we make tremendous amount of efforts to raise funds. However, we still raise relatively less funds than previous years. Well, ever since COVID-19, the amount of funding that we can raise actually drops. So we can see how the changes in economy also affect us as a workshop to support women. We really would like to thank all the companies who still manage to support WSCV in this time of difficulty. Thank Apple and Toyota, who are our platinum sponsors, and Cruise as our silver sponsors, and Mesh, Capay, DeepMind, and Snap as our bronze sponsors. So you can scan this QR code and submit your CVs to the sponsoring companies. And we will also share this link on Twitter, and we will display the QR code again later in the coffee break. So about our schedule today, our main workshop is from 8:30 to 1 p.m. And the dinner, we also have a mentoring dinner. It's an opportunity to meet other female computer vision researchers, and the paper authors will be matched with senior computer vision researchers to share their experience and career advice. So in the main shop, we have talks from invited speakers and oral presentations, and there will be a coffee break. And after that, there will be a panel session, and following by a poster session. So in the panel session, we have invited female experts from both academia and industry. You can scan the QR code to submit your questions, and we welcome topics including computer vision research, diversity in computer vision, and about career advices and work-life balance. We really would like to thank everyone who makes this workshop possible, and especially our organizing committee. Yeah, so if you have any questions, you can email us and follow us on Facebook and Twitter. So with that, I finished my presentation, and I would like to introduce our first speaker, Professor Angel Chen. Professor, you want to set up for the talk? So Dr. Angel Chen is an assistant professor at SFU and a Canadian CVPR AI chair. Her research connects language to visual and 3D presentations and grants language for embodied agents in indoor environments. She has worked on synthesizing 3D scenes and shapes from natural language, as well as localizing objects in 3D. Her work has been recognized by awards such as the SGP Dataset Award for ShapeNet, ScanNet, and the TUNIS Hans Fischer Fellowship. So welcome, Angel.
Thank you so much.
Set up the Zoom screen share.
Thank you so much for inviting me. And I just want to check so everyone can hear me and the Zoom is good. Okay, great. So today I'm going to talk about connecting 3D and language. And before I start, I just want to say a few words about what I do. So I think I work at the intersection of language and 3D. So that's why I'm going to talk about language and 3D. But in addition to that, why am I interested in this is because I think it can be very helpful for us to build helpful AI assistants that can help us around the home in the future. And with that, I also do a lot of work on trying to develop large-scale interactive environments for training such assistants as well. So let's first take a brief overview about what can we do with language and 3D. And one thing that's very exciting to see is that there's a lot of work now that's collected to these two modalities. So I'll just give some quick examples to start. So one thing I'm interested in is 3D content generation from natural language, and that's what I will hopefully talk about if I have time. But let's start with some examples of that. So early on, I worked on text to 3D scene generation, where we would take a sentence, parse it into kind of a graph structure, and then basically figure out where things would go, in the sense of that, okay, you should be placing this chair exactly here, the table here, and so forth, and do retrieval. And in addition, I've also worked on text to shape generation, where we would basically, this was back in, I think, 2017, 2018, where we would learn the joint embedding of text and shape spaces. And then you would have this encoder decoder model where you would then be able to use this joint embedding for both retrieval and text to shape generation. Other things that you can do with language and 3D, in some ways, this is the same things you can do with language and 2D, but now we just extended the third dimension. We can also take 3D representations, such as a point cloud of the scene, and we can have a sentence such as a black chair in the corner, it is next to the table, and try to have a model that predicts where it should be, which of these objects in the scene would be that chair. And this I will talk a bit more about at this I think open domain reasoning workshop in the afternoon. And this is very useful for robotics in the sense that, you know, if you wanted the robot to go to the black chair in the corner, you first need to locate where it is. And you can also turn this problem around and turn it into a problem where you want to detect objects, and then for each object be able to figure out what description, how should you describe each object. And we've established a set of community benchmarks to help people evaluate progress in this field. So the task of localizing objects in 3D, we call the scan refer, and the other one where we want to caption objects, we call scan to cap. And there's benchmarks that if you're interested in working this to basically evaluate different methods for doing these two tasks. In addition, we have a language for 3D workshop that will be happening at ICCV. And so you should consider submitting to the tracks. And this is part of a larger community. So there's also other people who do work in this space who are developing, you know, slightly different benchmarks. The referred 3D benchmark is developed by panels. So not by me, but it's very similar. And then they focus more on being able to not just locate objects given a description, but actually trying to see if you have a set of similar objects, can you actually figure out which exact one you're specifying? Other tasks you can do is 3D VQA. So this is, again, a straightforward extension of 2D VQA to the 3D domain. But this, I think, may be my first visual of what a 3D point cloud would look like. So here you do have the 3D information, which is a little bit different than if you were to work in 2D, and you would be able to, like in 3D, you would have actual separation, physical separation between the object. And so you can ask questions like how many chairs are there, and you can, if you were to understand a 3D scene, maybe figure out there's 8. And with a single view 2D image, you may not be able to see that, just because in 2D, you are, the field of view may be limited, and maybe you only saw 2 chairs. While in 3D, if you had a complete reconstruction of the scene, you would be able to more accurately count. And again, there are other works in this area as well. Around the same time we were doing 3D VQA, there were several concurrent work that came out that also developed data sets and for evaluating 3D VQA. The other thing I work on is embodied in the embodied AI area, where we have an agent that can take actions in your environment, and that's the agent takes actions in the environment. What the agent sees and the state of the environment actually changes. And one simple, I don't know if it's really simple, but one task that people study in this area is called vision language navigation, where you would have a set of instructions that you would want the agent to follow in this environment. And this is maybe this is a top-down view of some recent work we did in this, in the sense that what you want to do is when you have an agent follow instructions in this environment, and you want to make sure that the path that the agent follows actually follows the path that corresponds to that. More recently, we've moved on from just doing navigation to actually also doing both navigation and manipulation. So you have this task where you have sentences like move toy animal from chair to table. And there the idea is that the sentence follows this form where you want to move some object from some starting receptacle to or ending receptacle. And this requires not just navigation, but manipulation as well. And here's an example of a robot that goes and actually does this. And this is our ongoing NeurIPS 2023 challenge, which I encourage you to, if you're interested in this area, to check out. And you can then, and this is, I wouldn't say it's easy, but there are simulation platforms that are provided for you and starting code, and so you can give it a try. Okay. So this is kind of the first part of my talk, where I give a brief overview of what kind of different tasks you can do with language and 3D. And then I'm going to talk a little bit about, this is a very high level view of how do you develop models that do this. And the key to this is, so nowadays, everything is represented. Okay, there's a couple of things that happen now. We all use deep learning, and then we have a common representation space that we use, basically vectors. And so that allows for this easy fusion of modalities. And you may also have seen diagrams that look like this, where you would take text, encode it into some latent space representation. You take another modality, such as image, encode it into the latent modality. You have some fancy module in the middle that somehow combines it, and then from it, you can then stick different prediction heads that does different things. Does the image and text match, predict captions, or you can do actually operations on the image as well. And this is very similar if you were to go from text and 2D images to text and 3D, you will basically just replace the image encoder with a 3D encoder, and can do very similar things. But one thing nice about 3D is that once you have the 3D, you can actually generate many different views, 2D views of the 3D data. So you can not only apply 3D encoders, but you can also combine that with image modalities as well. But the key magic that happens really is about how do you actually align these representations. So when you say the word cat, it actually corresponds to the visual features you would get from either your image or 3D encoder versus just being very far apart. Now, many of you are probably have heard of CLIP. And so CLIP uses contrastive loss to basically learn this joint embedding space between text and images. And this loss actually was introduced in a slightly early, well, it was actually built, there was a bunch of work that built up to this, but there was an earlier paper that introduced this notion of this symmetric bimodal loss, where you would have this contrastive loss between the text and image. You would have positive pairs among the diagonal, and then the other ones where the text and the caption you can draw randomly, and they would form your negative samples. And this was and the symmetric version was introduced in an earlier paper. But you can basically take the same idea and you can apply it in 3D. Again, now 3D, one thing about 3D that's a little bit different from 2D is that you have choices, a lot of choices in representation. I showed you earlier where there was a 3D point cloud of a scene, but you can also represent your 3D input as voxels. And then there's other choices as well of like, what information do you have for your voxels? Do you have them colored, or do you have them just have only the occupancy? Or, do you represent also a little bit about how far each voxel is from the surface? Similarly, for the point clouds, you can have all these different kind of choices in representation. But as I was saying before, once you have 3D, you can then also generate from the 3D shape itself. You can also just take different views. And here you can take not just one view, but you can take multiple views. And then, so usually when you work with 3D, you have this option of also aligning the 3D features with a bunch of 2D images, potentially from multiple views. And this will allow you to have these embeddings that are lying between the 3D representation and the 2D. And of course, now if you were to combine all of these together, then you can basically have this trimodal embedding where everything's potentially aligned. And the nice thing about working with 2D is that you can leverage pre-trained images, and also as well as languages, you can leverage pre-trained text encoders, and you can leverage text and image encoders, because one thing about 3D is there's much less data for 3D, while for images and text, there's just a lot more in the world. So here I will go briefly describe a work that we did recently last year, well, last year or the year before, depending on how you count, where we actually just take this simple idea of taking these 3 different modalities and learn joint embeddings that combine the 3 of them. And again, there's different choices you can make, not just in what the input is, but as well as what do you have, how do you extract these features? How do you take the raw input and create an embedding for it? In this case, this was from, I guess, several years ago. So we used a very simple bi-directional GRU for the text encoder, a multi-view CNN for the images, and a 3D CNN for the 3D shape. And then we just combine all of them. You can also, if we wanted to leverage 3D pre-trained 2D and text embeddings, then we can take CLIP, and then we can replace the bidirectional GRU with a CLIP text encoder, and we can replace the multi-view CNN with this CLIP embeddings. And then you'll notice there's a little bit of view pulling in order, because we have multi-view images to combine them. And this you can use for a variety of different applications. You can use this for shape generation, but in addition, you can also just use it for text to shape retrieval. And I do believe that in the future, text to shape retrieval will also become more and more important because we'll have more and more 3D content. Right now, 3D content, there isn't that much, but you all see there's a proliferation of these generative models, not just in 2D, but also being able to generate 3D objects, 3D scenes. And we also have these improved scanning capabilities. So you can take a cell phone and you can quickly scan or object and create a 3D version of it. And so that means there will be more 3D content and you will want to do text to shape retrieval as well. And here again, just as another way to visualize what we're doing with our trimodal embedding is that we're taking these different modalities, kind of embedding them into a joint embedding space. And then the contrastive loss we use will basically pull things that were labeled together, and things that weren't labeled together apart. And then once you have that, then for retrieval, you would just measure the distance in the embedding space. And here's a quick example of the learned trimodal embedding space. You can't really tell it's really trimodal because I don't really show the 3D, but you can imagine each of these images represents not just the 2D image that you see, but also a 3D shape as well. And you can kind of see the different kind of chairs are kind of in different places, and the different tables are also pulled apart. And so we took this method and then we revisited the earlier work where we actually had a fairly complex way of creating this joint embedding space between text and 3D. And we took this and we revisited this. And we were able to show that with this very fairly simple contrastive loss, we were able to outperform prior work that was basically much more complex. I'm not going to describe the original text to shape like joint embedding because it just was kind of complex. And then as well as part to word, which relied on part level information. So we didn't rely on any of that, and we were able to outperform that for the purposes of retrieval. And here we show that with the trimodal embedding, where we learn the embedding between images and voxels and text, we're also able to outperform the bimodal ones. We also compared a version of the clip. The clip one that I show here is only a bimodal one. So it's very possible if you take that and combine it with voxels, it can do even better. But because of the limited amount of data we have, it's also interesting to see that our bimodal variants with just image is able to have similar performance as the clip plus MLP. And it could just be that the data is fairly small and that the language we're working with is also very simple because most of this is just tables and chairs. While if we move to something with like certain categories, then the clip using pre-trained embeddings really helps because that has in such a diversity of shapes and things that weren't found in our training data. And this kind of work is getting more and more popular now, especially as the 3D world discovers language and models such as clips. So now having their own variant. And so this is not my work, but I just wanted to show you just quite a bit of work recently, point clip, ulib, OpenShape, that's all trying to do this with text and images, as well as different kinds of representations for 3D, often point clouds. And so this is an exciting time to be in this area. In addition, there's also work that does this with 3D scenes as well, not just focusing on single shapes, but there's quite a variety of work that looks at especially open vocabulary, because this is what the pre-trained embeddings allow you to do. It leverages all this information that's not available in the labeled 3D data. So this is pretty exciting. If you're interested, you can come talk to me. Yeah. So the last part of my talk, I'm gonna talk about how do you create 3D content from text. So this was something I was interested in earlier, but that seemed like very, very hard. But now again, due to the development of better generative models, more data, as well as the development of neural radiance fields, it's kind of lots of people are entering this field. Yeah, and so there's this work from 2022 called Dream Fields that basically used CLIP to learn this, to basically try to optimize a NERF so that it can generate nice 3D representations that can have images that are similar in the CLIP space to the text. So here with this work by one of my students, we basically investigate what kind of augmentations do you really need to train this well, because it actually happens that the CLIP landscape is very very finicky. So again, as a quick summary, what we have is we have the pre-trained image and text similarity model, and we have NERF models where you basically have a 3D representation that basically for which you need to have a neural network, or you have to have something that predicts for each point what's the color and density. And that allows for differentiable rendering, so it will allow you to generate an image, and then from the image you can have compute features, 2D features, and then you can compare the similarity of the 2D features to your text in the CLIP space. And if you optimize that, you can then get a pretty good, potentially a pretty good 3D representation that matches the text. And so what my student did was he tried to investigate, how do you make this much more efficient so it can be run by more people? And he actually used compared the explicit voxel grid. So these voxel grids are much more, can be much more, take much less memory versus implicit voxel grid. So for the implicit voxel grid, what you do is you have a little MLP that predicts the density and color for each point. And it's a voxel grid because we only predict it for at the grid vertices, and in between we would do the interpolation. And then there's various losses that we would add, or there's some loss we'll add to encourage the object to be, condensed into coalesce into a single shape. And then there's other different augmentations you can apply. And the main part again is this CLIP similarity, where you try to have the encoding of the rendered images match that of the text. And and those are the main components. And then I'll show here some different examples where we found that having the spherical prior that he introduced was very important for the network to train. And maybe it's really to optimize, because these are per prompt tuning, in the sense that you have a single prompt, you train your network for however long, and then a single 3D representation comes out. And so the spherical prior is pretty important. And then this, I didn't explain too much about the different augmentations, but most of them help. And you can, this is just more about this, but basically, depending on the augmentation, you can have these very much more detailed images that, or 3D representations that come out, and you get rid of the noise. And here are just some more pictures that we are indeed generating this 3D models. One thing that you have to be a bit careful is that depending on the CLIP model you use, it may also have different performance. So there are CLIP models with, ResNet backbones versus a VIP backbone. The VIP backbone, because it has little tokens and little patches, it actually works much better. Okay. Yeah. And he also had comparisons of explicit versus implicit voxels, as well as the original Dreamfield work. And you can see that compared to the original Dreamfield work, our work, there's much more details and more fine details. Yeah, and here are just some more examples where it rotates. And just as a comparison of how long, again, this is for every prompt. So every sentence that you want to optimize, you kind of give it the input and it will train the little nerve model. So we were able to, get the original dream field was took about 2 hours. We were able to get it down to like 21 minutes, and you were able to fit it into like a little commodity GPU with 7 gigabytes. So it's something you can do too, not just Google. And I just have a couple more slides. And then again, just tons of work for after that, start in 2022, 2023. So there's tons and tons of work. At the same time, it's very exciting, but also maybe a little bit intimidating, but still encourage everybody to work on this. And I think having efficient training is still an issue. And then, also having a model that is not per prompt, and there's some work in that. These are 2 examples of work that's maybe not necessarily per prompt. I just end with some challenges in 3D content creation. Evaluation is still a big open challenge. Is the generated content high quality? Is it diverse? Does it actually match the text? I think existing evaluation metrics are poor. And how do you characterize, what can this, you have these models, what kind of things is it good at? What mistakes does it make? Can't handle like these relationships. I started with a little graph, does it handle these relationships correctly? And again, how do we generate this 3D content efficiently? These are all open challenges, so it's very exciting. And I just want to conclude by saying there's many different challenges, and it'll be, lots of things, exciting things to do here. Okay, I probably ran over, but so.
So we are a bit over time, so maybe you take one question quickly. So anyone have a question? Okay, I can ask the question. So you were mentioning about contrastive learning and using contrastive learning and data. So one problem, maybe it's more general to contrastive learning, not to 3D data. Like it's sometimes we lose the semantic information in contrastive learning, like two items belong to the same class sometimes are assigned as negative.
Yeah.
So how you
solve this? So it really depends on how you set up your positive and negative pairs, right? Because so there's contrastive learning where you use classes to say, okay, they should belong to the same they should be positive versus negative. And then there's contrastive learning, like CLIP, for instance, is just saying, does this image and a sentence go together? And that allows you to have a finer degree of finer details about, the meaning. But in addition, if you look at a sentence, it's also compositional. And so you can also start to have a contrastive learning. And some people do this when they do it not just at the whole sentence level, but they start to do it at the maybe the token level or the patch level for image. So that's one way that you can get this maybe finer grained, like where you start to retain some of the semantics of the little pieces. Yeah. Okay. Yeah. Okay.
Thank you very much. We are now going to have the first oral speaker for the paper for this workshop, and Paris, and presenting sign language translations based on the instructional videos.
Hello. Sorry, we cannot hear. We cannot hear you at the room. Oh.
And so they have a limited vocabulary and translation. So for example, the most used is the Phoenix dataset, which has roughly 10 hours of video. So in our work, we focus on translation, but on the how to sign dataset, which is a more complex and larger dataset that contains over 80 hours of videos, and it has paired videos and translation. So this dataset, it has been used to do sign language retrieval and sign language video generation, but it has not been used to perform sign language translation. So state-of-the-art works, as I mentioned before, they focus on these datasets that they have a restricted domain, but they achieve high BLEU scores, which is the metric that we use to evaluate machine translation. Recently, more bigger and more complex data sets such as OpenASL or How to Sign have been released, but this has impacted. So we have seen a drop of performance for the sign language translation models. So in this work, we are introducing the baselines for sign language translation on the How to Sign dataset. And the way that we do this is that we tackle this task as a sequence-to-sequence model. So this is, if you have worked with machine translation, this is very similar to what it's done in machine translation. So we have a transformer encoder-decoder that is able to generate text, but in our case, we need to condition it with video rather than with text. And this is actually an active research field within the sign language research community to find the best way that we can actually tokenize these videos. But the way that we do it is by using inflated 3D ComNets. And this is a model that was introduced for action recognition, but that we further fine-tune with sign language data. But similar to machine translation models, we also need to tokenize and lowercase the text. And then we use a typical encoder-decoder transformer architecture. So in order to evaluate it, we use BLEU score, which is a widely used metric in machine translation, and it compares the predictions of the translation with the reference. And so the higher, the better it is. However, we realized that since our dataset contains instructional videos, there's these frequent patterns that appear, like I'm going to show you how to, and this inflates the BLEU score, even if the translation has a different meaning. So in order to solve this, we introduced reduced BLEU. So this is inspired by the work on the machine translation workshop. And the way that this is computed is that we remove these frequent patterns and then compute the reduced BLEU score. And this translates into a better correlation between a higher metric and a meaningful translation. So our results, we got a BLEU score of 8, which is still low, but comparable to datasets of similar complexity. Then we have an example. So we have the input video and then the reference and the prediction that our model has. And this example shows that not only are we able to translate these frequent patterns, but also some meaningful words like moments of defense. And then this other example shows that the importance of really focusing on the reduced BLEU metric to select the best checkpoint, because if not, the BLEU score is still high, even if the meaning is not the same. So yeah, basically in this work, we proposed the baselines for sign language translation. We found that using these alternative metrics works better to select the best checkpoints. And our final contribution is that we make our code, models, and also the features available. So you can check them in the project page, and this is everything. Thank you.
Thank you, Mel. We are not able to take a question, unfortunately,
Okay.
because we are over time.
Mhm.
So we can ask there in the poster session in details, everything. Thank
Yeah,
you.
thank you.
Our next presenter is going to be Roberto. Thank you. It's going to be a presentation about underwater detection using an end-to-end encoder decoder architecture and graph search with aggregated and reflector. And the presenter is going to be Megha Kapoor.
Good morning, everyone. My name is Megha Kapoor, and today I'm here to present my paper, Underwater Moving Object Detection using an end-to-end encoder-decoder architecture and graph search with aggregator and refactoring. The flow of my presentation is as follows. First, I will give a brief introduction to underwater surveillance and underwater moving object detection. Then, I will move forward to the motivation of the proposed work, proposed method, and graph search algorithm comes next. Finally, I will conclude my presentation with results and discussion. As we know that the water covers around 71% of the Earth's surface, so detecting and tracking marine life is very important. The process of detection of moving objects in an underwater environment by assigning a label as either a foreground or background is known as underwater moving object detection. The state-of-the-art moving object detection algorithms uses an encoder-decoder architectures where an encoder is used to extract the features and a decoder is used to detect moving objects. The primary motivation of our work is the idea that there is a loss of information in the encoder-decoder network due to the presence of pooling layers. Further, the CNNs have an assumption of spatial symmetricity, which is not valid in high-dimensional space, which may not be Euclidean space. If we consider image as a graph and decompose an image into three channels R, G, and B, each node of the graph can be initialized as a pixel. Considering an image of 2 to 4 cross 2 to 4 cross 3, there will be around 1 lakh nodes at first iteration, computing which is very tedious and computationally intensive. The proposed method consists of an encoder-decoder architecture to extract the moving objects, and no refactoring is done in the latent space. The encoder comprises of convolution layers and pooling layers to extract the features of the object. In between these layers, prelude activation is used. At the end of the encoder, the matrix is flattened to obtain a latent vector. This latent vector is projected into graph space using graph sage. Graph sage consists of two parts, graph sampling and aggregation. In graph sampling, node relations are built based on the information carried by the nodes. In the beginning, the nodes are initialized randomly, and during training, the connections are pre-built iteratively. There are different aggregator functions to compute the average information shared with the next node. There are two symmetric operators, mean and max, which don't change the output based on the order of the nodes. Then there is a non-symmetric LSTM operator which treats the information as a sequence. The refactored vector is fed to the decoder to project the information from latent space to image space. Decoder consists of convolution layers and upsampling layers. At the end of the decoder, sigmoid activation is used. To train our model, we use binary cross entropy as the loss function, and to optimize the parameters, Adam is used. These are the qualitative results. Here, column A contains the frames from the Fish for Knowledge dataset. Column B contains the corresponding ground truth. Column C to column H depicts the visual results of 6 state-of-the-art methods, and column I contains the visual results of our proposed method. It is clear that our method can retain information by preserving the shape and structure of the object. For quantitative analysis of the proposed work, we use 5 different challenges from Fish for Knowledge data set, where analysis is performed with 3 aggregator functions in terms of accuracy, precision, recall, and F-measure. Here we found out that the mean aggregator functions perform better than max and LSTM. For a more descriptive analysis, please refer to our paper. These are few references, and thank you.
Thank you, Meghna. Unfortunately, also we cannot have any questions, but please send her your questions virtually. Our next presenter is going to be Devi Bari, and she is a research director in generative AI and at Meta, and an associate professor in the School of Interactive Computing at Georgia Tech. Before this, she was a director in the Fundamental AI Research Fair Lab at Meta, and her research interests are in computer vision, natural language processing, embodied AI, human AI collaboration, and AI for creativity. She's a recipient of many awards, including the NSF Career Award, the IJCIA Computers and Thought Award, and she got an award for Outstanding New Assistant Professor, and she's also recognized in the Forbes list of 20 incredible women advancing AI research. So welcome, Devi.
Thank you.
You have in HTML. No, it has
Join a Zoom call or anything, or So do we need to join a Zoom call or anything, or this should just be fine?
No.
Okay, sounds good. All right, thank you. Thank you for the kind introduction and for having me, and it's good to see everyone here. So I'm going to be talking about multimodal generative AI, or as I often like to call this, AI for creativity. And so the work that I've been doing in generative AI has been on the media side of things. So things like generating images, generating video, generating audio. And obviously we don't want to be generating random images and random videos and random audio. We usually want some way of controlling what is being generated. And so these models often take the form of taking in as input text that describes what we want to generate, and correspondingly generate these different modalities. And then if you're taking in as input text, you can think about other ways of controlling this also, right? Like for image generation, you might want to say, well, I want to describe what I want in text, but also give you a sense for what the layout of the scene is that I'm looking for, and generate an image associated with that. For video, maybe you want to take text and an image as input, and you want to animate the image based on that text. For audio, you may want to use audio prompts. And as you might be able to tell, sort of going forward, you can envision these models that are looking across all these modalities, right? Text, images, video, audio, 3D, that Angel was talking about, and having ways to sort of have these systems that seamlessly go across all of these modalities. And I think that would be quite exciting. So before I get into some amount of detail of the work that we've been doing, I thought it might be useful just to kind of do a little bit of a historical recap, and it doesn't even go that far back, right? Like this is still just like within the decade, but there's just so much that has happened here that it's easy to forget the pace and where we were not too long ago. So this was kind of what for a lot of the GANs and things like that was often focused quite a bit on faces. And when we had seen this progress, you were like, oh, wow, the progress is tremendous, right? We were all already very excited. And then beyond faces, if you go back 5 years or so, this is just sort of somewhat of an arbitrary paper that I picked from 2018. These are the kinds of images that we could generate, right? Like I haven't shown you the text prompt here, but you can see that it's somewhat compositionally kind of makes sense. You can probably get what the semantic category is. But as soon as you kind of pause and look closely at any region, things are quite wonky, right? Like they don't look very realistic. And then in 2021, which surprisingly many people I think still forget that like there was this big moment in 2021, right? When DALL-E 1 had happened from OpenAI, and it was these images that we were all shocked by, right? Like we thought these were amazing. And when I was trying to make these slides, I went back and I'm like, wait, I thought it was better than this, right? Like, and this is what happens because there's been so much progress after we had, and this was amazing, right? Like avocado chairs, right? That was one of the canonical examples. These different styles of images that you could get just by prompting it in, it had blown all of our minds. And this was 2021, so about 2.5 years ago now. And then 2022 happened, right? Like there was much more craziness in this space then. I like to remind people for obvious biased reasons that Make a Scene from Meta was in March of 2022. Then DALL-E 2 from OpenAI happened just 10 days after that. And then Imagen from Google, Party from Google, Stable Diffusion, ControlNet, like I haven't been making this slide for all of the months that followed. But yeah, there was this huge explosion of amazing work coming from many different institutions, including academia. So this is kind of where we are. I'll go a little bit into some of this. For example, for Make a Scene, this is what the architecture looked like. So it was these token-based models and autoregressive model on top of tokens on text. This intermediate representation, which was a representation of the semantic layout of the segmentation map of the image, and then followed by the image. So this was the sequence of tokens. And so if someone gives you as input a piece of text, you would first decode what the semantic layout of the image should look like. And from there, you then decode what the pixels should look like. And so that was one of the sort of the key ideas in this work of having this intermediate scene representation, which we found improves the quality of the images that are generated while using less data, because there's a stronger inductive bias here, right? So you can get away with less data. We had this emphasis on trying to get the objects to be less wonky, so having these losses specifically around different objects. And perhaps the thing that I was most excited about was that this intermediate scene representation, even though our original motivation was to make the image quality higher, it was a really, really nice way for a user to control the generation more, because instead of giving just text as input, you can give the text as input, and instead of the model inferring the scene layout, a user can be providing the scene layout as input, and then from text and the scene layout, the model can generate the image. And so based on the sketch, based on the composition, you can get different images for the same input text, which I thought was something that was quite neat. And so here's what that would look like. So you can sketch out and say that this is where I want sky, this is where I want some grass. I want some mountains here that look roughly like that. I'm drawing a tree. And then notice that I'm drawing flowers in the sky, and you'll see how that gets interpreted. A beautiful painting of cactus glowing at night in front of mountains on green grass. And I think I said starry night. And so those flowers kind of got interpreted as these stars in the sky. And you could have used the same exact sketch, but with different text, where it now says a cactus on lush green grass in front of snow mountains on a sunny day with roses in the sky. And that same layout, but gets interpreted differently based on the text. And so here are more examples from Make a Scene. At the bottom left, you see the sketch that was given, and you see the images that were generated, including sort of fairly fantastical things like these two-headed zebras on bicycles where the wheels are made out of pizza and things of that nature. Yeah. And so pushing more on this control, what we did was we gave some AI artists and some non-artist Meta employees access to Make a Scene. And we sort of asked them how they liked sort of having this control over the generation. We showcased some of the art that they had made. Some of the Meta employees worked with their kids to create these various depictions. And that is kind of what we put out there. So here are examples of things that we showed. So again, for the same sketch, having these different images, the pixels look very different, but the layout is very, very consistent, right? So you really have much more control over these images than you would if you were just putting in text. This is one of my favorite examples where it's sort of just you're drawing just one object, right? And the text is saying it's a colorful sculpture of a cat. And based on the different shapes of the sketches, you're getting these sort of 3D like sculptures in these different poses. And so, yeah, I think it's kind of, it shows you the value of the text itself, right? Like saying that this is a 3D colorful sculpture, that's hard to describe. It's going to be hard to sketch something in 3D, but then the shape of what pose you want, that's much harder to describe in text, and so that you can convey in the sketch, and those two kind of come together to give you these generations. This is just for a reminder that the sketch is optional. This model can also just do your classical text to image generation by inferring the scene tokens along the way. And this is an example of that. These are just sort of other visuals from the different artists that we had worked with. So the artists were Scott Eaton, Alex Rubens, Sofia Crespo, and Refik Anadol, which was, and it's sort of delightful to see. It's 4 artists, right? I'm not saying these are like millions and millions of people or anything like that, but it's still delightful to see somebody using the tools that you've contributed to, seeing what their experience is like, and sort of getting a very different perspective than what we might on a day-to-day basis talking to other researchers and engineers kind of thing. Not that there's anything wrong with researchers and engineers, but it's sort of, yeah, it's still a good perspective. So by this time, sort of as DALL-E 2 Imagen had come out, sort of there was much more focus on diffusion models. We had been working with token-based models, and we started investing more in diffusion models. And so here's one piece of work using diffusion models with the specific idea of trying to leverage retrieval. So what happens is during training, when you have an image, you find its k-nearest neighbors and condition the generation on those to generate the image. And then at test time, you can, if you have text as input, you can replace the image encoder with a text encoder using something like CLIP that Adrian was talking about earlier. And now, again, you can then retrieve images from some database that you care about, and from there do the generation. And so there's a few things that is nice about this. One is you can get away with a much smaller model because now you're leveraging this data set of images. So all your capacity doesn't have to be in the parameters. You have a lot of information in the data set that you're working off of. You can get away with unpaired corpora because at training time, you're only using images. And then at test time, you're using these CLIP embeddings to kind of swap the text in. And so you actually didn't need unpaired data. You didn't need paired data. And the third thing that's really nice is that you can adapt to new styles. At inference time, if I bring in my data set of photorealistic images, then I'll be able to generate photorealistic images. If I bring in a data set of paintings, I'll be able to generate paintings. If I bring in a data set of stickers, I'll be able to generate stickers. and you don't have to retrain your system, right? Your system stays the same. And so here are some delightful stickers. And the ones on the right are kind of nice, like you can do these manipulations on top of an existing sticker. So you're saying that I want this kind of avocado, but I want it with red lipstick now. And you can do those manipulations, which is nice. We also done some work on using latent diffusion models, in particular with personalization. And so here are examples. I won't go through the technical details of this, but where you can bring yourself to an image, right? So if you have your avatar that you've created, you can describe a scene. Maybe you're on the beach or you're on sort of in the Swiss Alps, and you can bring yourself to it. And so here are various examples of avatars that have been inserted into generated scenes. These are not real images in which you're bringing them. And so the pose of the avatar gets predicted, and then it's rendered based on whichever avatar you're choosing to depict. All right, and so looking at video generation a little bit, this is the high-level architecture where from input text, we have a model that generates 16 frames for across 4 seconds. So that's 4 frames per second at low resolution at 64 by 64. And then there's a series of sort of super resolution, both spatial and temporal, that get added on top to get you higher resolution and higher frame rate images. The key here is that we very directly leverage text to image generation models. So this prior that I'm showing you here is initialized with text to image generation models. So before we do any training, when the 16 images are generated, they're all decent looking, valid images, just that they are not temporally coherent because the model hasn't been trained on video at all. So it is generating 16 frames that all respect the text and all look reasonable, but are not temporally coherent. And so the only thing the model is training, is trying to learn after that is to make these frames temporally coherent. And for that, it is going to be using just unsupervised videos. So videos without any labels. And so the idea is that from text to image data sets, these paired text and image pairs, the model learns what the world looks like, how we talk about it in natural language. And then from unsupervised videos, it learns how the world tends to move. And those two things come together to be able to generate videos from input text. Right? And so what's nice is that even if your video data set doesn't have all these fantastical things of unicorns and things of that nature, because you're leveraging your text to image models, all of those styles, all of those fantastical depictions, you directly inherit all of that. You get to benefit from all of that. And like I said, you don't need any paired video data, which is also nice. And so here are some examples of videos that are generated about 4 seconds long. A dog wearing a superhero outfit with red cape flying through the sky, horse drinking water, a golden retriever eating ice cream. Many people find the hand pretty creepy. It doesn't bother me a whole lot, but yeah. Here's another one. And these are, I don't have all the text prompts here, but here are several other examples of generated videos. And I mean, yeah, I've looked at these a whole lot, but it's still kind of those, like the input is just text, right? You're putting in words, and all of these pixels across space and time are being generated. And I think that's really amazing. This was one of the examples that I think people found quite fascinating. 2 kangaroos are busy cooking dinner in a kitchen. A fluffy baby sloth with a knitted hat trying to figure out a laptop. And you can, in some of them, you can kind of see the frustration. For some, there's more patience. Here's one where from, like I was saying, you can take as input an image and you can kind of bring it to life. You can animate it. Here's one where you can take 2 images and sort of try to tell the story that happened between them. So you're interpolating between these 2 images. And then you can also take in as input a video and generate multiple variations of those. And all of this is off of the same kind of core backbone that I showed you for the model architecture earlier. And so that's for video. For audio, I won't get into the technical details, but here's an example of what you can do. The input text is what you see at the top. Oh, no. Is it? The input text is what you see at the top, and the output is the sound that is generated, right? So if you say a car driving on the street, you expect to hear the sound of a car driving on the street. Right, I think you get the idea. And then it's sort of a natural question, right? Well, you can generate video, you can generate audio, can you put them together? And the answer is yes. This is not a very sophisticated putting them together. It's literally just concatenating the two. We generated video, we generated audio. And the reason we can get away with just concatenating is because these are such short video clips that you can't really tell that things are out of sync, but there is no sync here, right? Like it's just two independently generated modalities being put together, but it would make a lot of sense to figure out how to do this in a way that is synced. But I find that sort of adding just audio, music in this case is sort of adds to the delight of it quite a bit. And so that was 2022. a lot was happening. Just quickly in how am I doing on time? Okay. And so in early 2023, which we're like in the middle of it right now, but we took Make a Video and pushed it to 3D. So very relevant to the kinds of things that Angel was talking about, that from input text, so from a prompt, generating what you see here. And so you can either think of it as 3D video in the sense that you have a video that you can view from any viewpoint, or you can think of it as animated 3D content, right? Like you could have generated the static dog, but now you can see it animated. And so we've been calling it 4D, but a lot of people find 4D confusing. And so, yeah, whatever you feel is better. And so the basic idea, and I'm glad that Angel's talk was just before mine, where in 3D, you saw some of this work where there is work like Dream Fusion, for example, that uses text to image models as prior, and then optimizes the parameters of a nerve to generate images that the text to image model is happy with, right? And that's how at inference time, you have this procedure to generate static 3D content, and a very similar idea, but now with video, right? You can generate this 4D content by using text to video as the prior. And I showed you the Make a Video work that we had to optimize parameters of a dynamic nerve. So it's not generating just 3D content, it's generating dynamic 3D content or 4D content to generate videos that the text to video model is happy with, right? And so this is also an inference time procedure. So there's no 3D data that the system has seen. As you saw with Make a Video, there wasn't any text to video data that the system had seen. So this is all based on paired text to image data and unlabeled videos that we can generate this 4D content. And there's no training. It's a purely inference time procedure, which is really, really expensive, but there's no training involved here. And so one last thing that I want to end with, and it's on my mind a little bit because there's a workshop later today on sort of how can academics deal with the fact that a lot of work is being based on large models and things of that nature. And so I just kind of wanted to plug this, where this was early in 2022, if I remember correctly, that we've released this closed world that has these various characters that do various things that interact with each other. It's a synthetic world, so every pixel has a semantic label. We've collected text annotations. We have added audio to this, and it's basically a video game, and we've added audio to it. And so the data looks something like this. So there's a couple of different themes here, and it's open source. Everybody can be building on top of this. This is just sort of what we had added to it, but it's 375,000 video clips. It has audio, video, text, and pixel accurate semantic segmentation maps. And you can study sort of all sorts of retrieval and generation problems. And so when we first started studying video generation, it was within this closed domain, with the idea being that if we can't generate videos in the closed domain, there may not be much hope in the more open world. And so going from 4 seconds, if you start thinking about 15-second videos, half a minute, 1 minute, you want characters. If you saw the videos, they're mainly kind of animated images, right? Not a whole lot was happening in the scene. But if you want to think about characters interacting, leaving the scene, coming back into the scene, you want consistency in appearance, all of these problems, I think, make a lot of sense to study in a closed world. And then whatever those findings are could be carried over to these larger scale models. And so that's something that you're welcome to check out if you're interested in this space. So to summarize, I've talked about generative models for a variety of different modalities. Some maybe common themes across the approaches that we've taken is this idea of accelerated learning. And so wanting to leverage generative models at lower dimensionality to build generative models in higher dimensionality rather than sort of starting everything from scratch. So using text to image models to get to video, using text to video models to get to animated 3D or 4D content, trying to leverage retrieval-based approaches so your generative model doesn't have to have all of the capacity. It can be coming from data sets that you might have. Something that I'm particularly excited about is user control, that if these models aren't doing what you or a user want them to be doing, then they're going to be useful only to a certain extent. And so finding ways to get more and more of this control, I think, is interesting. A whole bunch of open problems. Text faithfulness doesn't always work. There's big gaps there. Visual quality, the videos that I showed you were 512 by 512, and 768 by 768. It's only 4 seconds long, not much else. If you try to go longer, the videos get quite a bit worse. Multimodal models, like I hinted at the very beginning, that these are still sort of individual models for individual modalities. There's no reason why it needs to stay that way going forward. Evaluation, which is something that Angel brought up as well, that it's hours and hours of researchers and engineers sort of staring at these images and videos to get a sense for what works and what doesn't work. And there has to be better ways to be able to do that. A huge sort of scope of work on bias, how if there's all of this content that's being synthetically generated, what that means for our various ecosystems of information. Adapting models for specific use cases. Everything that we talk about is sort of this core foundational capability of text to some modality, but then depending on what it is that you want to use it for, what is the work that needs to happen, how do we make these easily adaptable, how much data do you need for fine-tuning this, what do you lose as a consequence of that fine-tuning? I don't think any of that is well understood. And finally, like I said, just more and more control would be good. So with that, I'll end. I'm excited about this space because of the potential that it has for sort of enhancing human expression, human creativity, and I'm happy to take questions. Thank you.
I'm Alessandra Sala from Shutterstock, Senior Director of AI and Data Science, and the Global President of Women in AI. So I'm delighted to be in a room with so many women. Sorry, I was a little bit late, but this morning. I know the word mega. A couple of questions. I like the approach of learning from text to image and then moving into the video space. And the technical question is, where is this going to, right? We heard the ideas that you guys may have to actually improve the quality of those videos. So digging more into the image space or leaning into the video space?
Yeah, I think it's both. What we found over and over again with these text to video models is that whenever the text to image models get better, the videos also get better. And so I think sort of still staying on top of all the advancements that we're making with images and making sure that we're bringing them into the video generation models, I think will continue to show benefits, at least in the short term. We'll probably hit that ceiling soon enough. The bigger, more video specific piece is in motion, and in particular with large motion. It's often the case that in these, like I was saying, that in these 4-second video clips, there isn't a lot that's happening. And finding the right data sources where that motion can get richer and richer, and figuring out how to have models that can do that well, I think is an open problem. So whether it's sort of hierarchical representations that at a course level for sort of have the frames across, maybe it's going to be a 1-minute video, but you just have 16, 24 frames that capture the whole thing, and then you interpolate from there, or if there's some other way of doing it. I think those are all open questions. Yeah.
Very much the hierarchical approach. Another question that I want to take from those amazing women here. Coming, more question. It's an amazing space.
Hey, Doc. So I wanted to ask a question about the last work, the Mugen work. So you described like how the rationale for that was that you wanted to like limit the scope and work in like a closed setting, and then eventually your open findings will translate into the real world. But how much do you think the nuances kind of carry over to the real world? Like, for example, in a video game format, it's like 2D, there's like a black screen in the background, there's no real kind of 3D world in it. So do you imagine that the findings that you find by following kind of that direction will translate, and what do you think will be the steps we need to take in order to?
Yeah, I think that's a very good question, and I completely agree that we have to be very careful with what is it that we expect to carry over. So you're right in the sense that the fact that it's a 2D world, it's not 3D, you're not seeing different viewpoints, there's sort of very minimal, simplistic occlusions and things like that. And so anything that we try and transfer from the appearance of what the world looks like is most likely not going to generalize. But my hope is, and I don't have evidence for this, but my hope is that if there are sort of hierarchical representations that we develop, or if there are sort of consistency losses that we figure out, that when a character disappears, and then when the character appears again, the character should look the same. So that kind of sort of representations of memory, consistency, whatever you want to call it, those kinds of ideas, if we carefully develop them, may have a shot at generalizing to the open world. But yes, we have to be very careful with having a very clear sense of what is it that we expect to generalize and checking that often enough. You don't want to be spending 2 years sort of overfitting to this very close world without testing anything in the, and similar like in embodied AI, there are these discussions also, right? Like what do you expect to transfer from simulation to reality? And you want to be doing those experiments along the way. But yeah, so that's how I'm thinking of it.
Thank you so much.
And another thing that, for example, that could be valuable is the audio video sync part that I was saying, that right now we've generated them independently, but any work that you do to figure out how do we generate these modalities in sync, those ideas will probably generalize, and then you'll have to retrain it on real data to be able to actually work on real data, but the idea itself may generalize depending on how it's been done. Yeah. Right.
Thank you for your great presentation. I wanted to ask also about the longer videos. If the bad effects that you see are sort of jittering or inconsistency that we see in other text video generation works, or is it?
So the jittery effects that we see that can happen even with shorter videos sometimes, where even in a 4-second video, sort of in between frames, if it's not done well, then you might see those jittery effects. What we have seen for the longer videos is more sort of objects starting to deform into something else, like that consistency of appearance not being maintained. So for example, this is not a great example, but I'll give it because it comes to mind. We have this one video of this teddy bear on a skateboard in Times Square, which for 4 seconds looks decent, for 10 seconds actually looks decent. And then when you get to 15 seconds, 30 seconds, eventually the teddy bear decides to kind of go off on the skateboard and its ear is still attached to the building that was behind, right? Like, and that's not even the worst of it. Like the worst of it is where the teddy bear would just sort of evolve, deform into something like a car on the street or something like that, right? Like those kinds of things. And we just haven't figured out what is a good way of keeping all of these frames be reasonable, and not just individual frames, of the transition across frames, because a teddy bear on its own will look fine when it's evolved into a car. The car on its own might look fine, but along the way, this shouldn't have happened, right? Like there has to be, and that is something that hasn't been fully figured out. And so that's not quite the jittering effect. It's just like keeping the video consistent. Yeah. Thank you. Hi.
Thanks a lot for the talk. I also kind of wanted to follow up on the long video generation. So when somebody is used, have you guys thought about it using a longer video? So I think a lot of video sets for training right now has been just like 10 seconds or like 20 seconds. So maybe that's it. One of the I wanted to know what do you think about.
Yeah, I do think data is a bottleneck in these things, and it's even if you have a source of data that you're using from somewhere where there's a whole bunch of videos, figuring out how to appropriately sort of slice the video up so that there aren't sort of scene cuts in it, Depending on the source, if there are people who've put sort of all sorts of text on the video, how to sort of not have that be. So just having high quality, clean data that is longer and longer videos, I think I think it will take work to figure that out. I do think that even in shorter videos, it's not a solved problem yet. And so I do anticipate that we'll probably keep seeing some work even in the shorter videos. It's not at the stage, like with text to image models, we kind of expect that if you put in a piece of text, you'll get somewhat reasonable images. It's not always going to work. I'm not saying image generation is a solved problem, but there's some sort of, we can expect that it'll do reasonable things. I don't think we're quite there even with shorter videos yet. And so, yeah, I think both of these threads will continue, but data is a big open question there as well. And it's not quite what you were asking, but I think even in terms of how willing we all are to invest in just putting in the effort and time and energy into just getting good data to train from, is I think is a bit of a mind shift that we all need to be adjusting to, because a lot of the power of these models comes from good data that's been curated, rather than like, I think someone said it may have, yeah, I shouldn't get into the controversy of it, but like whether it's the model versus the data, I think all of us tend to lean towards modeling and we don't sort of like investing enough in data, but I think data is a big part of it. So to your point, I do think that that will be an important piece of longer video generation. Yeah.
Thank you very much. I think we are kind of behind schedule, so thank you very much for the interesting talk. And you can still ask both our speakers questions during the panel. Yeah, now we would like to invite you to a sponsor discussion. So we have some sponsors outside. You can talk with them, and you can study your CVs and everything. And you can also collect your workshop. And we will continue at 10:10 for the second oral session.
Are more consequential than ever, and our responsibility for making the right choices has never been more profound. At TRI, we hope to develop technology harmonious with people's everyday lives, technology that marries the highest potential of both human and machine to bring forward a world with less conflict and more opportunity for everyone to lead deeply happy and meaningful lives. TRI is a place that is working on some of the most challenging problems that are facing humankind today. And this ranges from climate change all the way to world peace. We honestly feel here that with some key technological breakthroughs, that we can help drastically reduce the amount of carbon dioxide that's emitted into the atmosphere in a way that is affordable. And on the other hand, that we can help with understanding and predicting what human beings do to tremendously advance the way they interact with each other.
At the company level, there's just a philosophy of what is the impact we can have on humanity? And really, I think Toyota thinks at that scale. And our mission has really stayed very centered in the sense of human amplification. How do we use AI to amplify humans and not replace them?
Toyota has this really aspirational goal of producing happiness for all. The researchers that we've brought on to work on this amazing mission with us, which is to create human AI technology that can actually improve the collective well-being for people, but also our planet. It's a really big charter and an ambitious goal. And the team really believes that the people that work on this also feel inspired by this mission.
It's really important that TRI keep itself at the frontier so that we have the potential to discover the breakthrough that will lead to some kind of leap, either in a capability that Toyota has or in a new market of other products. One of them, as an example, is the robotics field.
Robotic technology can be used to amplify many parts of human life, whether it's assisting people who maybe have lost the ability to perform certain tasks, or to be giving them a service, to be helping them around the home to do things that they no longer want to do. But we still need to develop the robotic capabilities to do this. We feel like robotics has the potential to be a major contributor to the solution to this challenge.
Another area of intense focus for TRI is energy and materials field.
The work we do in the energy and materials division is important to me because we're really trying to solve one of the grand challenges of our time, which is how are we going to move people around without relying on fossil fuels?
Within the energy and materials team, there's incredible research taking place at different size scales and different time scales. So we have incredible researchers that are working on innovative solutions to find new materials that can be critical in helping battery technology become more widespread.
TRI's machine learning team grew out of our need to build AI systems to perceive the world.
Principle-centric AI is how I describe our approach to machine learning. Machine learning is very data-centric, which is what is the best data and how much can I get to teach the machine through example. You tell the machine what it should learn from those examples, the supervision, and then you have that scaled enough that it's gonna work well in new conditions. But in the physical world, you have limits. So experience gets compressed into principles, and these principles, we can distill it. And all that is how we learn as humans, and it's missing from machine learning today. Humans are so much more complex, and so we need to have something else than just data, than just equations. But we need something in there, just as principles, this distilled form of experience.
Human interactive driving is about making driving both more safe and more fun at the same time.
What we're trying to do is really marry more traditional robotics techniques, things like model predictive control, image detection, with sort of more data-driven learning-based techniques. So trying to meld the best of sort of the newer techniques in machine learning with some of our more traditional techniques in robotics to get the best outcome.
We can envision a new style of interaction of AI and vehicles so that we can keep the human empowered in a car, but while keeping a very high driver engagement, while using all the tools of robotics and AI and automated driving, of perception, prediction, and planning to make people better drivers, to make cars safer, and to improve the driving experience.
The human-centered AI team, using these techniques like machine learning and AI, but applying them to problems that really have to do with human beings.
The HCAI Research Division is a multidisciplinary group of researchers that come from the backgrounds of behavioral science, machine learning, and human-computer interaction. And we believe that these are all really important contributions to human-centered AI.
I think that the kind of work that we're doing here at TRI, which is fundamentally human focused, it's using AI techniques applied to human beings in many different contexts. We use real science, real technology at the highest state of the art in order to try to make breakthroughs in those fields. And I think we have a pretty decent chance of doing so.
To the constant beginners who sing off key against the beat, to those unfamiliar with convention, unmoved by rules, and reborn with every new discovery. Those open to daydreams and night dreams and visions and mirages, who can see the millions of shades of green in a field of grass. Whose days are filled with mysteries that cannot be solved with facts. You are more powerful than you think. And you are welcome here.
Actually being able to make money by creating posts. But there's a problem. It's the very images that the posts are generated by AI. It's hard to work. And if you want to change this life environment, it's just like if you're up there, I think it's
Last year, yeah. Yeah, I'm I also have I want to like talk to people, but yeah, yeah, that yes, yeah, so that but yeah, the last year the last concession. Yeah, and it's on purpose. Maybe they go unsuccessful and continue to I'm especially this book is also this is so yeah I'm in yeah.
Yeah, you can present from your I put the camera up here. Okay.
Yeah, posters now?
No, we are starting over again.
Sorry?
Okay.
So we're starting the second oral session now. We're going to start with Sabrina and presenting dense multi-task learning for reconfigure comics.
I only put it here because the chair cannot move around.
So hope all of you are enjoying the session as well. Moving it forward, let's talk about comments, shall we? Something that all of us have enjoyed at some point in their lives. Before I begin, I'm Sabrina from CVPR, Switzerland, here to present dense multitask learning to reconfigure comics. So comics reconfiguration is the task of transferring comics from paper to digital devices that span different screen sizes. For instance, the input comics paper image on the left over here. All right, yeah. When resized to a phone screen, squeezes the contents of the image to make the contents fit onto the phone screen. However, if we identify important characters and objects in this image, and then transfer them to the phone screen, we can maintain the essence of the images as it was intended by the comics artist. Here, for example, the Smurf character is kept as it is, and the house is reduced in the area. Note that even this relatively simple example takes more than an hour to deconstruct and reconstruct. We thus need to find ways to automate this process. To automate this process of comics reconfiguration, we obtain dense predictions, namely segmentations of characters and objects, as well as their depth. This contrasts with the existing methods in comics analysis, which are camera detection, shown in red over there, character recognition, shown in yellow, and the speech balloon detection, shown in blue, and so on. None of the existing methods over here, they reason about the dense pixels, which bring a lot of information for reconfiguring these comics. We therefore use our dense prediction techniques, cues, that are integrated with an off-the-shelf retargeting algorithm to ultimately reconfigure this comics. And this will in turn help the comics authors, as well as the comic industry at large, to diffuse their work across diverse publication media. So how do we achieve this? Our work builds on the following modules. The first one is an unsupervised image translation method that reasons about instant styles in a scene. This separately trained translation module gives comics images that are translated in the style of the real images. The image translations are then encoded and decoded by a transformer-based multitasking module using a hierarchical window configuration to predict the segmentation and depth maps in the comics domain. We train this multitasking module in a weakly supervised manner, where we leverage real-world ground truth annotations. However, bridging this domain gap just by the translation module gives unsatisfactory results, since the task features, they do not transfer well across the two disparate domains. We therefore introduce a domain transferable attention mechanism in our framework for effective task transfer between the disparate domains. So what is it about? The domain transferable attention mechanism integrates the task feature of the real domain into that of the translated comics. And to this end, we employ the token level domain discriminator, D-token, that matches cross-domain local task features, where N is the number of task tokens, D-token is the probability of the task token belonging to the comics domain. During adversarial learning, D-token tries to assign 1 for a feature token belonging to the comics domain, and 0 for those belonging to the real domain, while GF produces fake comics tokens. So conceptually, if you might think of it, a higher value of D-token for a task token in the real domain, it applies higher transferability to that of the target token. So we measure the transferability of a task token by this function over here, the task function, where H is the standard entropy function. And this transferability allows us to leverage the task tokens from the real domain that are learned via full supervision, thanks to the available real-world ground truth annotations. We then inject the transferable task tokens from the real domain into the self-attention weights computed in the comics domain as follows, where Q is the query of the feature token from the real domain to that of the comics domain. The K token is the key token, basically, which will aid in the transferability. This is the Hazelnut product, and this is the concatenation operation. Now, obviously, the softmax operation over here, it indicates the discriminative semantic features between the two domains. And the concatenation, indicates the transferability of each of these tokens. So one is discriminating, and the other one is governing the transfer between the two domains. We then pass these features through Boolean norm and MLP operations to compute the intermediate features in each of these transformer layers. Now, that was a lot of technical information, but the good part is, if you see it qualitatively, when applied to the translated comics, our method shows quite nice results, outperforming the baselines. For example, the depth of the comics characters in the background are more pronounced, and this helps to segment these characters more accurately when compared to the baselines. For more qualitative as well as quantitative methods on comics such as Tintin, Spirou, please visit our paper or as well as our poster. Now, we finally applied the dense predictions method to an off-the-shelf image retargeting method to see whether it's feasible for reconfiguration. We see that our method is able to preserve the semantics better
while overcoming structural distortions by the classical scene carving method, which is also a retargeting algorithm. You can look into the areas with the red circles in there. Now, for some test comics panels, we see that our method achieves retargeting well, although it's blurry because of the normalization coming from the retargeting algorithm itself. Similarly, this is another example of retargeting, and in summary, we first use unsupervised translation method to translate the comics to the real domain, which allows us to leverage the ground truth annotations from the real domain. We then encode the translated comics features into our multitasking module, showing the use of complementary tasks for dense predictions. Thereafter, we formulate a domain transferable attention method that basically bridges the domain gap between these two disparate domains. And ultimately, we see the feasibility of applying the developed method for retargeting of our comics and panels. This work was supported by the Swiss National Science Foundation and his team. Thank you so much for listening, and I'm open to questions at this time. Thank you.
You were very much for your presentation. We're a bit behind time, but we have time for one question.
My question was just how sensitive is this to different styles of comics? Like, do you find it works better on some versus others?
It does. So this is quite generalizable across the different artistic styles of comics, except when it's black and white.
Oh, okay.
And also when the panels have too much text with them. So you need to have like a text removal method and then do this entire retargeting.
Awesome.
Yeah, thanks.
Thanks again. Our next presenter is going to be a virtual presenter. She will present perception over time, temporal dynamics for robust image understanding. And her name is Mariam Daniel.
Hello, everyone. My name is Mariam Daniel, and I'm glad to present our work entitled Perception Over Time, Temporal Dynamics for Robust Image Understanding. So a little bit of background here. Psychophysical studies using EEG and fMRI have shown that recognition happens over time in the human brain, around 150 milliseconds is the time that we understand the gist of a picture. Hello. Everyone, my name is Mariam Danieli, and I'm glad to present our work entitled Perception Over Time, Temporal Dynamics for Robust Image Understanding. So a little bit of background here. Psychophysical studies using EEG and fMRI have shown that recognition happens over time in the human brain. Around 150 milliseconds is the time that we understand the gist of the picture, and we may need longer time to identify individual objects or even longer for the semantics of the scene. These studies show that this process happens in a course-to-find manner, starting with a very general understanding, and as the time goes by, we may understand the details. Even when we're looking at static and simple scenes, there are feed-forward and feedback mechanisms in the visual system, as well as other parts of the brain. On the other hand, standard deep learning models often have a single feed-forward pass, and there is no notion of perception over time. In this work, we are interested in figuring out what this difference causes. So for the motivation study, we asked two questions. How do off-the-shelf deep learning models classify CTF presented input? How do humans perform on a similar task? We use a subset of ImageNet for our analysis in answering these two questions. To convert the static images into a sequential format to represent the course-to-find information, we use three methods. First, we designed a sparse coding model that tries to mimic human perception. We also use two approximators that are not bio-inspired nor have a time component, but they're computationally efficient: JPEG compression and Gaussian smoothing. This is a sample set of coarse-to-fine decompositions we used in our experiments. The task is to detect what's in these images, starting from a blurry image all the way to fine-grained information. In the beginning, you probably didn't see much or had multiple options in mind, but there is a certain time that we get confident in our decision and see these hints. So now let's take a look at how these images were generated. We use a multi-layer sparse coding model that simulates our visual system when we observe an image. It has several layers that all together generate a reconstruction at each time step. We refer to this model as RSCD. We see an example output of each layer. Suppose the image on the bottom left is the input. Then we have coarse-to-fine images from top to bottom, resulting in the reconstructed image over 400 time step. The three components of our model, ITE, that does the holistic understanding in the brain, V1 that does the fine-grained information such as edges, and V2 the in-between, compete with each other and collaborate on generating the reconstruction in a way that's very close to the input, but is using the least number of components based on the sparse coding constraints. In this image, you can see example reconstructions over time. In the first row, we use the bio-inspired sparse coding model, RCD, to generate images over 400 time steps. Here we have time step 10, 25, up until 400. We also have JPEG reconstruction and Gaussian blurring. They don't have a time component, but the order of reconstructions represent the coarse-to-fine information. We chose 10 different qualities for each experiment. For the motivation experiment, we took ResNet 50 for our baseline and evaluated its performance over time. The solid line represents its accuracy on the original images. And when we asked it to classify the decompositions over time, we saw at early time steps, low quality and not human understandable images achieve incorrect but confident predictions. Also, we don't see any steady increase, neither in the accuracy nor the confidence over time with higher quality images. We see the accuracy on fully reconstructed images is still lower than the original images. We examined some other off-the-shelf models. Here we have ResNet 152, Inception and Exceptions. These models do pretty well on the original images, more than 76% accurate, but they perform similar to ResNet when it comes to decompositions over time. Then we asked the human participant to take a similar test. At each step, they needed to report what they see and how confident they are. As humans receive more information over time, both their accuracy and confidence improved, which is in line with our original hypothesis. These results motivated us to design a model that would perform similar to humans and could benefit from the information given over time. So here we looked at solutions that instead of treating images as static data, could detect objects over time. I wanted to see if that could improve upon conventional techniques. For this experiment, we created a dataset with 30 randomly selected classes from ImageNet. Our model takes an image, generates its coarse-to-fine decomposition. Its backbone, shown in gray, is a ResNet model with only 2 trainable layers. And at each time step, our model classifies the decompositions, but also has access to its understanding from previous qualities using LSTM or 1D CNN recurrent units. For example, at Q5, it has access to its representations from quality 4 all the way to quality 1. We hypothesized that this could improve the accuracy and robustness. So here's a snapshot of our results. We see that conventional techniques, even state-of-the-art vision transformer, VIT, do not surpass 80% accuracy on our test data. On the other hand, our proposed CTF models have reached to 98.9 when using either JPEG or RSCD decomposition. Next, we evaluated our solution from the robustness perspective by running adversarial attacks. We use white box attack, PGD, to the level that ResNet F30 reaches only 15% accuracy, and also black box square attack. There is a sample image of each algorithm on the right. Our results show that CTF processing is more robust to these perturbations. Also, more interestingly, our CTF model is more accurate on attacked images than conventional techniques on original images, compare 85.8 with 79.5. In terms of computation efficiency, CTF models requires 1/3 of the number of trainable parameters required for transformer models such as VIT-based, thanks to the capabilities of perception over time. Now, let's take a look at the importance of coarse and fine information. On the left, we see the performance of ResNet and our CTF models when gaining data. seeing better quality images at each step. All quality levels mattered. They helped getting better performance. See the frequent increasing pattern on the left. For JPEG and RSCD, using only the first 6 qualities were enough to top ResNet. On the right, we see the effect of losing data. At each step, we are removing one course level input, and we see that they really were helping the CTF models to do better. Although even quality 9 and 10 alone were sufficient to top ResNet. We also see that JPEG and Gaussian approximators are not always stable. This shows that how bio-inspired components in the RSCD help with robustness. Would like to evaluate a proposed technique on larger data sets, possibly with more diverse perturbations. Another work could be evaluating the effectiveness of CTF processing on other tasks, such as segmentation and identification. Thank you for your time. Please feel free to reach out with questions.
So unfortunately,
I'm unmuted. Hopefully they can hear me online. So after living in Southern California for a while, I moved up to Berkeley, which is where I got most of my degrees, my bachelor's and my PhD. And this is a nice photo of Berkeley. This Campanile clock tower is kind of very famous. It's very, very tall. And Berkeley is super proud of it. And one thing that they're proud about is especially that that clock tower is taller than the one at Stanford, which I also attended as a postdoc. So I got to experience both of them. After my postdocs, I did a year at Facebook, now Meta, working in their Menlo Park office. This is a photo of one of the beautiful quads that they have available to you there in order to enjoy the lovely weather outside. For the last few years, I've been at Georgia Tech as an assistant professor. We also have a clock tower. It's even shorter than both of the other two. But regardless, my trajectory through these different places, I've kind of sampled a few different universities, a lot of them in California, worked a little bit at a company. So we won't have time to talk about more of that in this talk right now, but of course at the panel session, we can discuss that later. I also want to right up front give a big shout out that one of the awesome things about having an academic career is being able to mentor and support a lot of amazing students. Here's some photos of the people from my lab currently. And there have been a lot of others that have come through over the years. Okay, so now we can dive into some of the research. Today, I'm going to be talking about two projects, and broadly, they fit into the space of trying to design and develop computer vision systems that are efficient and reliable. So we can get started first with the efficiency problem. And this is motivated by this idea that we have available to us lots and lots of large models. Of course, if we think about those available to us for download, there's lots of different models used. We have PyTorch, we have Tectron, we have lots of different places where people have pre-trained models. And of course, those models have been trained across a variety of different data sets. And what's awesome about this is that we know we can take these models and we can repurpose them or we can reuse them for new settings. And of course, each of these models across each of these data sets is also could be trained across a variety of different architectures. And the latest and greatest architectures, the ones that are working really, really well, are computationally expensive. So if I, as a practitioner, developing some application area, I want to be able to download one of these models that are freely available. I want to be able to use it for my particular application, but I might be limited in that the model out of the box may not fit on my GPU. It may not fit my real-time specification of my application. So in order to help combat that, we want to be able to help improve the efficiency of a model in order to make it more computationally tractable. And we're going to do that by reducing redundancy. The second part of the talk is addressing the reliability of the models. So let's say I am a practitioner, I want to download a model, I want to use it for a new purpose. I need to understand right away what are the scenarios under which I can expect this model to continue to perform as expected. So we'll address that in the second part of the talk. And instead of thinking about having a static test set that perhaps doesn't capture all of the scenarios that you would like to be able to represent at deployment time, we're going to consider what I like to think of as dynamic test sets. Okay, so let's get started with reducing redundancy. And for this, I'm going to talk about a work called token merging. It's led by a PhD student from my lab, Daniel Boya. And here's the general idea. With token merging, what we'd like to do is we'd like to be able to take an off-the-shelf model, a transformer-based model, and make it faster. So in general, if we have a transformer model, it has a set of input tokens, a set of output tokens, and some processing layers, each of these VIT layers in the middle. At a very high level, what we're going to try to do is we're going to try to reduce the amount of computation that needs to happen in those intermediate layers. And here's kind of the motivation or intuition of how we can get there. Let's say we have a VIT and we'd like to be able to recognize what's in this image. Well, what usually happens is you start by tokenizing this image and you process each of these tokens independently in order to finally come up with an output, like this is an orange. But you might think to yourself that
I'm gonna use my adapter. Everything can go wrong. All right, hopefully it will proceed smoothly. Okay, so here's what we have. We've added this tone block. We're going to use it in order to reduce the number of tokens that we need to process throughout the network. We're going to use it by a particular parameter R. For this, we're using a bipartite soft matching algorithm, and it looks something like this. We start with a set of tokens. We're going to randomly partition it into two sets, source and destination, compute similarities between each of these sets of tokens, and then keep only the R most similar connections. From those R most similar, we can now decide that we found tokens that present or adhere to very, very similar pieces of information. And so in order to reduce computation overall, we can go ahead and merge them. Now we have a reduced set of tokens that's specifically been reduced by R. Overall, we found that this particular matching formulation was very, very fast, which is something that we wanted, and allowed us to precisely control how many tokens are merged. So because today's talk is fairly short, I'm not going to present any more details. This paper is available online as well as the code, but I'm just going to show you some results. So first off, we can visualize what happens as we merge throughout the layers of the network. So this visualization is showing the first tokens that get merged all the way through to the end. And what you might notice is actually some of the things that get merged adhere to the visual properties of the scene that you would expect, like the fact that this hot air balloon, a large portion of it ends up getting merged by the end of the network. This model overall allows us to dramatically increase the speed of these visual transformers, in this case, 2 times faster for a VITL model with a minimal drop in performance, 1.7% accuracy. And that's without training. We can look at a quantitative analysis across a few different models. Here we have VITs of varying sizes. And what we're doing is we're asking what happens as we merge more and more and more. So the leftmost dot for each of these colored models is going to be the one that has no merging. And you'll see that as you merge, you can both increase the speed. You can see that as our throughput is increasing with a minimal drop in performance. So this is great, and this is without any training in the loop. You can actually integrate it into a training pipeline if you have ability and further reduce the amount of performance loss. And this is not specific to still images. We can actually use the same procedure across a variety of different domains, images, video, and audio are the examples I'm going to show today. In all of these cases, what we found was we can consistently get a 2 times speed up with very minimal drop in performance. And these are cases where you can see this type of performance speed up even without doing any sort of retraining. So just downloading an off-the-shelf model and inserting your tone block after your self-attention. There's an extension that's being presented later today at a workshop for stable diffusion, which also has code available. It's very simple one-line change in order to integrate token merging into your generation pipeline. Okay, let's move on to some visualizations. Here's some examples of merges that happen. Again, this model wasn't trained specifically to do any type of segmentation or merging. It's just something that happens naturally because these are the most similar parts of the image. So some things to notice is that a large portion of this gorilla is being merged together. But something like the face of the gorilla is being broken apart into different tokens. And even some small objects, like what this gorilla is holding, can be stored in their own token. Over here, what we have is 2 different similar parts of the image, even though they're not spatially connected, can still get merged together. And if we view this across frames in a video, what you'll see is, for example, this basketball gets merged across a bunch of different frames. But still mistakes happen, like the reflection of this basketball gets merged into that same token. So overall, the code is available both for the classification setting and the diffusion setting. It's something that you can do as a drop-in replacement to speed up your model. Okay, so the second project that I wanted to highlight today is that of dynamic test sets. And this project is led by a PhD student at my lab, Viraj Prabhu. The idea here is that we're motivated by the way in which models are usually evaluated. So usually we have a static benchmark, which is amazing for being able to compare lots of different models, lots of different training procedures throughout the years, and even within a year in a challenge. But once you get a model that's starting to have very high performance, you want to deploy it, you want people to be able to download it, you need to understand under what conditions it's going to fail. And it might be hard to do that with a single static test set where you're starting to get perfect performance. If we think about different application areas where we're going to have a wide variety of data that you experience at deployment time, we understand that it's not necessarily conducive to this static test set paradigm. So instead, we propose to have a way to probe a model through a dynamic test set. Here we have an example image. This is taken from the hard ImageNet test set. And the goal in this image is to be able to label it with the word dog sled. Okay, so we can take an off-the-shelf model that, let's say, we're considering using for our application. We want to be able to evaluate how well it works. The first thing you would do is on your existing test set, you would evaluate it against the category of interest. In this case, it is correctly predicting dog sled. The thing, though, is that the dog sled isn't really visible in this image. You see dogs, maybe you see a harness, you see a person in the background, and the model is inferring that there's a dog sled. Okay, so you might say that's fine. This is an instance of almost a positive correlation. The model has learned to pick up on cues that are positively associated with the category of interest, which helps it to be able to have higher performance overall. The problem is that if you just have that output here that says dog sled, you don't necessarily know under what conditions or what correlations this model will continue to correctly predict this class. So for that, we introduced this idea of generating language-guided counterfactuals, or LANs, where what we're going to do is we're going to introduce a set of changes to the image or edits to the image and see how well the model continues to perform. So for example, we might change the huskies to look like golden retrievers. And in this case, the model continues to be able to predict dog sled. Or we could change it to a labradoodle, where it's no longer predicting dog sled. And certainly in the case of a Pomeranian, it's not predicting dog sled. So this is starting to hint at perhaps there's some kind of implicit correlation within the model that has to do with the breed of the dog in order to make this prediction. And that's a valuable piece of information to have to be able to start understanding under what conditions the model will continue to predict the category of interest. So the way that this works at a high level is we start, of course, with the goal of wanting to evaluate an off-the-shelf model. So this model is frozen, it's already been trained to perform some task. It's also probably already been evaluated across a static test set and performs quite well. So in this case, it's accurately predicting howler monkey. What we'd like to do is we'd like to be able to understand under what conditions or what perturbations the model no longer continues to perform correctly. So the way that we do this is we're going to be using language as a structured medium to be able to perturb the image. We're going to start by taking a captioner. This is again an off-the-shelf captioner frozen. On this image, in this case, it produces a caption of a black monkey sitting on top of a tree with green leaves. We're then going to train by very small amounts of fine-tuning of a large language model to be able to produce structured perturbations to the caption. In this case, we might change the green leaves to be orange leaves and pass that through a conditional generation process to be able to produce the edited image. In this case, now we have that same monkey, but with orange leaves around it. And we can take this new counterfactual image and pass it through that same frozen model and see whether or not the performance of that model changed. In this case, it does. It's now predicting gorilla. And overall, in order to evaluate or dissect the information of a model across lots and lots of data, we might be able to just measure how much does the model change in response to some edit, some perturbation. Now, overall, there's lots of different ways that you could perform these edits. We choose to use a structured perturbation where the structure adheres to 5 different types: subject, object, adjective, domain, and background, and I'll show you some examples of those. Subject edit would be editing something that's in the foreground. In this case, we might be like the example before, changing husky to schnauzer. And in this case, making that change does result in a large change in the output predictions. Object edit might be editing an object in the background. So in this case, the monkeys are in a forest. It could be changed to a bamboo forest, which doesn't result in a change. Or you could have a background edit. So we could change the playground to be a snowy playground. In this case, we start to see model hallucinations. So previously, the model was correctly predicting horizontal bar, and now it's starting to predict things like ski and pole, which illuminates the fact that the model is very likely to be making inferences about predictions of skis and poles when you see a person with snow. The last example I'll give is that of domain edit, where you can change a photo of this monkey to be a sculpture. Now, all of these are performed programmatically. We're not manually defining the perturbations that should occur, but we can do this at large scale in order to start to monitor under what conditions does the model's performance change. And because this is an off-the-shelf tool to evaluate a model that has already been trained, we can apply it on existing models like ResNet 50, VITB, ConfidentXP, and CLIP, as shown here. So we can start by just evaluating these off-the-shelf models on a data set. So in this case, it's the hard image data set, hard image and other data set. And we can see that many of these models are actually performing quite well here. To make sure that our generation process isn't introducing too much deviation from the original performance, we can consider what would happen if we used our pipeline without changing the caption and just reconstructed the image. And we find that the performance of the model doesn't change too significantly, which is good because it means that we can kind of use this generation process in the pipeline without large concern that many of the changes in performance are due to just the generation process. You could consider variations of injecting perturbation into the language base, like random perturbations, where you select a word and mask it out, and then predict what word should occur in that mask. This results in some amount of changes in performance, but nowhere near as significant as our structured perturbation approach. Now, overall, what I've shown so far is being able to apply these perturbations at an instance level, but in order to make inferences about the model overall, you might consider wanting to make larger scale changes to a whole data set. One example of how that might work is with what we think of as category or class level perturbations. So for a particular ground truth class like howler monkey, I might take lots and lots of images of the howler monkeys, and I might consider a particular type of perturbation, like changing color in the image, and ask how often does this change result in some sort of performance change of my model at predicting howler monkeys. So the first image, I have a monkey and it's being predicted correctly with very high confidence. And we might consider taking the leaves and making them orange. In this case, it reduces the predicted performance and starts actually mostly predicting spider monkey. Now the next image, the model is actually getting incorrect. It starts out by predicting it as a black bear. If we change the ground to be pink, now it's starting to predict it as a howler monkey. So this is an inverse change where somehow changing the color is now positively impacting the performance of the model. And the last example is starting out correct. We take the green leaves and we make them snowy leaves. And this is an example where things didn't really change. So overall, all of these different variations are possible. And what we want to do is we want to look at it in aggregate across lots and lots of different examples for various different perturbations to find the ones that have the most impact on the performance of the system. So that's it for today. I just highlighted 2 different projects from the lab. One of them that focuses on efficiency, this token merging, and the other one that focuses on dynamic test sets. Together, we hope that there are steps in the direction of creating efficient and reliable models. I'll take any questions you have, and thank you for your time.
Yeah, thank you so much for your talking, and I'm curious about that how the token match process can actually speed up the diffusion process, because I understand how it can speed up the vision transformer because merging tokens is smaller than of the token sequence, but for diffusion model, because in my understanding the diffusion model still process the image pixel by pixel. So even you merge some of them, the total size of the image won't change. So yeah.
Yeah, that's a great question. And in fact, you need a lot more specialty pieces that I didn't have time to talk about today in order to make it work. You can't just use token merging out of the box. First of all, that will degrade the image quality too significantly. So there's a lot of different pieces that need to be added. But if you're interested in this, the lead student on that work is actually giving a talk just in a couple hours later today at the Efficient Computer Vision workshop.
Okay, thank you.
Yeah.
Thank you for your talk. That was really well done. Quick question on the last element of your talk. Can those techniques be used for maliciously the detection and the classification of those images? So with small modification, those labels can be completely off. So which are the insights that you would share with us? Which are the changes that are really driving those classification tasks so badly?
Yeah, that's a great question. And I think that that's the ultimate goal of this line of work, is to be able to make inferences like that. At this point, we don't have any sort of data set level insight that adheres across lots of different models. That's kind of ongoing work right now. This project with Lance was to be able to develop a platform that could be used for doing these types of perturbations so that we can start to infer. But I hope that it will be useful, and you should be able to also design other types of structured perturbations if you, let's say, have a constraint, as in the adversarial literature, that you shouldn't be changing the visuals of the image too substantially.
Thanks for the talk. So I found this class perturbation analysis story very interesting. And I'm curious whether different techniques to evaluate, so whether you do zero shot or linear probing, fine tuning, have large differences with regard to the effect of the perturbation.
So just to clarify, in this project, we're evaluating models that have already been trained. So the models that we focused on are the ones that I showed here. They've all been trained, many of them from scratch on ImageNet, or the CLIP model, of course, on the large CLIP data set. The only thing that's being trained here is the language perturber, and that's being done through fine tuning because we're leveraging a large language model. And then we basically just collected a very small, like couple hundred sample data set to help us to be able to teach the model what types of perturbations we wanted to make.
Thank you very much for your presentation. We're out of time, so we'll move on to the next presenter. We will skip the coffee break. And the next presenter should be in person, so I hope she's here. Sonia. Yes. She's presenting non-verbal communication cue recognition, a pathway to more accessible communication. Welcome.
Hello, everyone. Sorry, I'm Zaya and I'm from the City College of New York. And today I'm going to be presenting our work on nonverbal communication cue recognition, which is basically the task of identifying different sort of facial expressions, hand gestures, and body movement in a conversational partner in order to recognize the overall emotion in that conversation. So to start with, I want to talk about what our motivation for this project is. As you can see in this pie chart, about 55% of information communicated during a conversation is through body language. However, this information is largely inaccessible to around 2.2 billion people around the world, as they have some form of vision impairment. And because of this, previous research has shown that members of the blind and low vision community might actually experience some sort of conversational asymmetry where they understand the emotions and belief in a conversation differently than a sighted conversational partner might, as they are not receiving the same amount of information. So as there is a gap in this sort of understanding for the blind and low vision community, there has been a lot of previous research that has focused on this task. However, the previous methods for this task and the existing data sets have largely focused on just facial expression recognition instead of all the other modalities that could be used for this task, such as hand gestures and body pose. And they're very limited in scale and focus more on sort of general emotions rather than emotions that are more specific to conversation, such as like thinking, agreement. The existing data sets are much more general and cover emotions across a variety of different applications rather than just conversations. So to fill this gap, we are both working on putting together a data set and also working on putting together a model in order to recognize nonverbal cues in conversations. So I'm going to be stepping through both of these, starting with our data set. So we dubbed our data set the CCNY NVC data set. So far, it consists of 128 videos across 12 subjects and 10 classes. We built upon some of the classes that are found in previously existing data sets, such as happy and surprise, but we add emotions that are more specific to conversations as well, such as thinking, agreement, dislike, disagreement. And we also annotate across different modalities, as you can see in this picture. So we have a high level, like coarse-grained emotion label for each of the actions in our data set. And then we also annotate the specific actions for across facial expressions, head movements, and hand gestures, as all of those come together to create a nonverbal cue rather than just focusing on the facial expressions as previous data sets do. And since we are annotating videos, we annotate the start time of the action as well as the end time. Now, our goal is from this data set, there have been many challenges in putting together this data set. As you can see, here are some statistics on the number of instances for each class, the gender distribution and the age distribution, and you can see that they're very, very unbalanced. And this is a problem that occurs across many emotion recognition data sets. So as we are working on putting this together, we want to ensure that we are balancing not only the classes, but also the gender distribution, the age distribution, the racial and ethnic backgrounds of our participants, as all of these factors can really impact how you present nonverbal communication cues. And we want to create as unbiased of a data set as possible, which we can then use for our task of NVC recognition. And specifically, what we're trying to do is, given a video, can we both classify the nonverbal gestures? So individually, can we recognize the actions in each modality? And can we also then put these modalities together to recognize the overall emotion expressed by the conversational partner? In order to do this, we are using a 3D ResNet. And the idea behind using a 3D ResNet compared to a 2D ResNet, which is more commonly found in facial expression recognition and other emotion recognition tasks, is that since we are using videos, we really want to make use of like the temporal context in the video. And also because NVC, specifically nonverbal cue recognition, is not really a task that has been specifically focused on. It's mostly facial expression recognition tasks or separately hand gesture recognition tasks. What we do to kind of make sure that our idea is valid is we use our baseline model for the task of facial expression recognition on a large scale data set known as the FWILE2 data set. We present both our F1 score, the accuracy, and the official FWILE2 competition metric, which is a weighted average of the F1 score and the accuracy. You can see here that using our 3D resident model, we're able to beat the baseline and the second runner up in the competition by quite a large margin. We did not beat the top winner of the FWILE competition and are behind them by quite a significant margin. But it's also important to point out that the top winner on this competition used a lot of additional training data but whereas we're only training on the FWILE2 data set. And so we felt that this shows a good starting point that our model is able to learn and compete with current state-of-the-art models. And so from this, what we want to do is we want to expand our model into a more multimodal approach where we are making use of the hand gestures and the head poses to provide a more holistic understanding of nonverbal cues. And from here, I would just like to wrap up and talk about the main points and our main contributions. The fact that we're able to use our 3D ResNet model to get comparable accuracy on a facial expression recognition task, which has been widely studied, shows the promise in extending this for nonverbal cue recognition, which is something that hasn't been as deeply studied, but is very important considering the large amount of people around the world who suffer from vision impairment. And our goal is to take our current model and extend it into a multimodal framework for nonverbal cue recognition, ideally in the long run to create a sort of recognition aid that can be used in real time. In order to do this, we need a better understanding of how the different modalities work together, which is why this is our starting point in order to create a real-time recognition aid in the end. And I would just like to thank everyone in the audience and the committee, as well as NSF for funding this research. Thank you so much.
Thank you. We'll move on to the next talk. Our next talk is going to be a virtual presentation. It's from Sudo, and she's presenting a lightweight human eye fixation solution for smartphone applications.
Our paper title, Hello everyone. Today we are happy to present our paper title, A Lightweight Human Fixation Solution for Smartphone Applications. Myself Sudha Velusamy and the other co-authors are Rakesh, Anand, Narayan. And we are from Samsung R&D, Bangalore, India. Let's start by understanding what fixation prediction is. Fixation prediction is the task of detecting points or regions in an image that attract human observation's attention at first sight. For example, we have given a set of images and their corresponding fixation maps. You can clearly see that in any given image, the very important or salient object is the one which is rightly highlighted in the fixation prediction. So when it comes to a multiple solution present for understanding this human eye fixation prediction, most of the latest ones are deep learning based models, but they all come at a very high complexity and performance cost. So we are looking for designing a very lightweight network that can be suitable for real-time applications in the smartphone development. Before we start to understand the architecture of the proposed solution, it will be very interesting to know what are the applications of the human eye fixation prediction. Human eye fixation prediction has multiple applications, starting from object tracking, image composition, image retargeting, etc. For example, in image composition, there are various rules applied on a very particular or important objects by either positioning at the rule of third or by centering them or trying to understand their symmetry. So in this context, trying to understand the salient or fixation objects will be very much beneficial. Likewise, when it comes to smart crop, that is, given a large image, you would like to understand which is that exact object or region which attracts the human eye and trying to crop so that the focus can be emphasized. So for this application, fixation prediction is very much beneficial. We also present another application, which we call it as a smartphone lens switching. So given that latest smartphones have multiple lenses, starting from tele-lens, wide lens, and ultra-wide lens, a scene can be composed using all three different lenses to come up with a cinematic effect. To do this automatically, it is very important to understand in any given frame, what is the fixation portion. So accordingly, we will be able to move from the tele to wide, wide to ultra wide, and the anyway around the compositions. Now, let me introduce the proposed solution, which is the efficient fixation prediction module, which we call it as a EFNet. A lightweight fixation prediction network called EFNet includes two primary steps. The first one is a deep feature module. The module leverages deep learning techniques to extract rich features from the input data. By using a simplified multi-level feature extraction network, we can obtain context-rich representation. The second one is a union attention module. This module emphasizes significant and context-rich representation. By combining the information from the deep feature extraction module, it allows us to effectively capture diverse visual context and make accurate stage-wise fixation prediction. To detail out more, the deep feature extraction module utilizes EfficientNet as our backbone network. EfficientNet outperforms other modules like ResNet and BGT due to its superior learning capability and compactness. It offers scalability options based on accuracy and size, ranging from EfficientNet B0 to EfficientNet B5. EfficientNet B5, although it's larger in size, slower in inference time, it achieves the highest accuracy. Coming to the union attention module, the union attention module helps to emphasize the deep features by including the channel attention, which discriminate the significant channels in the feature maps. Likewise, spatial attention, which focuses on the informative region in the feature representation. The channel attention, the spatial information is mean pooled globally to obtain a representation value for each channel. In spatial attention, self-attention is used to capture the interspatial relationship of the features, and the input features are reduced to a single output feature map. In order to assess the effectiveness of our proposed EFNet, we conduct a comprehensive analysis and experimentation. We compared the qualitative performance of EFNet with other state-of-the-art methods, including EML-RES, EML-NAS, and MLNet. The table on the left provides the side-by-side comparison, highlighting the strength in terms of the qualitative performance. For the experimentation purpose, we use Salicon and MIT 1013 datasets for the training purpose. And to analyze the qualitative results, we have chosen to use unseen images from the Salicon dataset for our comparison. We observe that our model produces relatively smooth and consistent results. This leads to an increased hit rate and reduction in false positive. So quantitatively evaluate the engine, we use multiple metrics, but primarily the correlation coefficient and similarity metric. In this slide, we present some more results for your observations. So you can clearly see whichever is the important object or fixation object, they are very well mapped and they are very closer to the ground truth as compared to the other state-of-the-art methods. To measure the quantitative performance of the proposed solution, we examined the results using various metrics. The table demonstrates the quantitative evaluation, whereas EFNet outperforms other methods, especially in terms of correlation coefficient and similarity metric. These results clearly indicate the enhanced performance of the proposed solution. The proposed solution is designed to be very lightweight and efficient, enabling fast processing time. Our engine takes nearly 40 milliseconds per frame on CPU, 20 milliseconds on GPU, and it hardly takes 1 millisecond on the neural processor. The solution is optimized and deployed on Samsung S23 device for various use case applications, including smart crop and image composition. In conclusion, the paper presents a lightweight human eye fixation prediction network. The engine is highly robust for real-world data. We tested the engine on the Samsung Galaxy S23 smartphone device, captured images and video frames. The engine provides the best accuracy in comparison with the latest state-of-the-art techniques at a higher processing time. The improved inference time is nothing but close to 715 FPS, which means that it hardly takes close to 1 millisecond per frame. The engine is designed to be low model complexity, hardly around 15 MB as a model size, and hence it becomes highly suitable for low power and low memory devices like smartphones. We thank you so much for your attention. Thank you.
Thank you. If you have any questions, please join online and ask your questions on the online platform. So now we'll have our last invited speaker for today. It's Kristen Grauman. She's a professor at the Department of Computer Science at the University of Texas at Austin and the research director in Facebook AI research there. And her research is in computer vision, machine learning, focuses on video, visual recognition, and action for perception of embodied AI. She won also numerous awards, including the NSF Career and ONR Young Investigator Award, the PAMI Young Researcher Award, and several best paper awards as well. So welcome, Kristen.
Thank you. And then Zoom link, I think, is the piece I need to get. Right? You haven't seen to this video. No. Okay. Is that presenting? But you do have to sign to okay, so just share this one. Yeah. Okay. Well, hi everyone. Nice to see you here. I'm going to talk about some of our recent work, brand new work, really looking at human-object interactions in first-person video. Before I keep going, are we good for the Zoom capture as well? Yeah, well, good to go. All right, so thank you. So let me motivate why we care about first-person or egocentric video, first of all, and then show you some interesting things that we're trying to accomplish with it. So first, let's contrast with kind of mainstream, very important and influential data sets, many of which are listed here, that have really driven our field over recent years. Now, what do they share? They're typically third-person perspective of various human and object content that is from the internet. So it's kind of disembodied in that way. What's special about this data is not only, it's from the spectators or third-person perspective,
Plus, it's got this intelligence of being curated as a special moment in time that was worth taking a photo or video in the first place. So this kind of data is really driven and fed and fueled a lot of our today's models in a really important way. At the same time, we need to open the door to look at a very different perceptual experience, which is one that's grounded in the physical behavior of a person. And that's the kind of data I'm showing here, which is a wearable camera worn by a person doing some unscripted daily life activity that shows us long form video that's uncurated, right? It's everything that they see and over a very long period of time. And importantly, that's driven by and really reveals what are their goals and interactions and their attention. So stark contrast in terms of the just, superficially what the visual content looks like, but also stark opportunity for what you can expect to try and learn from this kind of data. So in our research, we're motivated by two different problem domains that at a glance might seem different, but actually share some important properties once you look at the perception problems. And that's on the left, robot learning, thinking about training the robots of the future to understand how to navigate and manipulate in our spaces that are created for people by watching how people do. And on the right, in augmented reality, we envision the assistants of the future that with our AR glasses on could give us just the right information at the right time because of what they understand about what's happening in front of us and everything that's happened before. All right, so then the examples I want to give you in the remainder of the talk are going to look at how we can move towards a fine-grained understanding of object interactions and in the wild, and especially egocentric or first-person video. The first one is going to be a hierarchical video language embedding. The second one is going to be also an embedding caring a lot about viewpoint invariance between what I just described as third and first person or ego and exo views. And then the third part, I'll show how we're looking at understanding when action and description of action actually align. And I'll motivate each of those a bit more when we get to each one. But let's start with looking at hierarchical video language embeddings. So here we have a resource in hand that is a project from many institutions over 2+ years time that we published last year in CVPR. And this data set is called Ego 4D. Ego, egocentric, 4D, meaning 3D plus time. And what it captures are glimpses of everyday activity around the world. And in fact, more than glimpses, because each sequence is on the long side for us in vision, 4 to 8 minutes long, even an hour's worth of capture from any given individual. In total, this data set has more than 3,000 hours of content captured by almost 1,000 different people from 74 worldwide locations. So it's very exciting for the diversity we see in the geographic location, the occupations of the people in this data set, and as you can see, a very rich hand-object interaction, showing some different kinds of manipulations. And furthermore, even social interactions. So a number of solitary examples, as well as social interactions with other people and even other animals. Now, the data set comes with benchmark tests. I'm not going to get into those in this talk, but it also comes with multiple modalities. So vision, audio, some 3D scans, I use stereo multi-camera, and important for my example here, text narrations. So every moment of this 3,000+ hours of content has been narrated in free-form natural language to say what the camera wearer is doing. So you can see examples of those narrations up top in white. C is the camera wearer. C paints with the brush. C dips the brush in the paint. C removes the fuel bottle, etc. Play by play of what they're doing in arbitrary language. That amounts to some 4 million sentences because there's about 13 sentences per minute of the data. Furthermore, there is a video level summary. And this is where it gets interesting for what I want to show you, because in addition to this play by play, every 8+ minute chunk of video has an overall description of what happened. We call that a summary. I'll show you an example on the next slide. So here's where we want to come in, is to create a representation that captures not just the what of what we see happening stage by stage, but also the why. And this, this is going to be a baby step in that direction, but this is so important for video understanding, right? Because what video offers us is information about how the world's changing, who's accomplishing goals, how are they accomplishing them, as opposed to only a snapshot in time. So to get this out of video, we need some new tools. And what we're looking at here is language as a tool that could help us to bring in that kind of higher level semantics. So if we were to start with the narrations themselves, as others have done in the field with some inspirational work that I'm highlighting at the bottom, then we could think about learning an embedding, cross-modal embedding, language vision together, that puts the descriptions close to the individual steps of the action. So if they say C fetches the water and it shows C fetches the water, get those close in the feature space. Where we come in is to also look at that higher level summary that gives the why. So across, in this case, 4 minutes of content, the overall summary says, well, C made some salad dressing. And what we're saying is this is really about the why, that summary. It's giving the higher level explanation of why all these different steps happen. And so our goal is to bring these two granularities or resolutions of representation together so that the one can inform the other. So to do that, we propose to train a hierarchical video language embedding. This is a paper appearing at the main conference this week, where at the child level, we'll do what I already described, say that these clips should be close to their descriptions. And then at the parent level, meaning that summary level, we'll say that when you aggregate over time, the textual descriptions, as well as when you aggregate over time, the visual descriptions in the full sequence, then their aggregation should be close to however you're going to encode that summary text, which is that overview description. Okay, so what this is doing is, on the one hand, saying, be like what you're describing, and on the bottom saying, be like what you're describing in the full sequence when you're talking about this overview description in text. So now we'll train both of these together so that they're informed of the other at both resolutions to get a single cross-modal embedding. We call this higher VL, higher for hierarchical and VL for video language. And to give you a snapshot, an intuition of what's coming out of such an embedding, here are TC plots on the left for the model I just described, and on the right for a precursor, this Eagle VLP, which does that clip level matching with the narrations. And you can see that here, the parent level summary text are the big circles and the child level are the small ones. And what we find happening as we've kind of imposed on this learning process is starting to gather up the representations of how those steps that are constituent to a given summary match with the summary itself. And that's something you can't get, of course, just looking at the step-by-step, play-by-play, instantaneous description of action on the right. So finally, we took this to make the rounds on different data sets. So they did different tasks dealing with recognition, anticipation, retrieval, and I'm showing you kind of the snapshot of all of those to highlight how robust this embedding has been for us across tasks and data set. So good results compared to state-of-the-art embeddings using video language, including baselines we developed that would have the summaries, but not use them in this kind of parent-child manner. And more details on this you can see on Thursday at the poster session. So now let's next turn to ego-exo alignment from unpaired data. And the motivation here is to go from coarse grain understanding of action, like are you brushing your teeth or are you tossing pizza, to very fine grain. So as you look at someone pouring water from a cup into a pan, what are the different stages when the liquid's starting to exit versus when pouring is complete? These are two different worlds of action recognition, both very important. We care about this fine grain so that we could do things like in robot learning or AR that I alluded to earlier, where you're really assisting or either mimicking or assisting in the step-by-step components of an action. It's hard though, because these things look so similar, right? If you're talking about when the liquid's exiting versus when it's not, that's a subtle visual difference. And viewpoint variation could be very large. In fact, we care a lot about a dramatic viewpoint change, which is what we can call in short ego-exo. So ego meaning, again, the first person, I see one set of things when I observe an action, and exo, when I watch someone else do it, I see a very different view. But we care a lot about linking both of those for the applications I already mentioned, both robotics and augmented reality, because in both cases, there can be an expert or a teacher or a demonstrator that we see from afar, and then we have our own point of view that we want to map the action from one to the other. So that's a strong viewpoint change. A lot of visual content doesn't survive or isn't at least non-trivially matchable between the two, but we care a lot about being able to align them. So here's where our method comes in. We propose an ego-exo alignment model, again, for feature learning. So we're going to get a better encoder, this time at the frame level, for fine-grained action representation. And we achieve it by doing some temporal alignment between ego and exo views. So on the top, there's an ego view of someone playing tennis. Here's an exo view of someone else playing tennis. And what we want to do is during training, learn how to align those two in such a way that rather than, an original encoding that would more or less only see what's similar based on the related viewpoint and cluster them accordingly, we want a representation where the ego and exo viewpoint change is kind of extracted away. And so if you're lifting the racket like this in ego, it should be similar feature when you look at the same thing in exo. And we want to do this so that the different phases of that action are also aligned. So lifting the racket here is looking different than putting the racket down here. If we did that, then what you could expect is an embedding that looks more like this, where over time, the shading indicates trailing off. They're aligned, and furthermore, the viewpoint change is collapsed. So that's a goal. And this is not the first time to look at trying to learn video viewpoint and variant video representations, but what's really important about our mission here is we want to do this with unpaired video. Unpaired meaning we won't have the luxury of both an egocentric camera being there and an exocentric camera being there and then trying to learn that alignment there. We'll have video over here that was captured by people playing tennis with a camera, a wearable camera, and then video over here where it was, on TV, whatever it may be. And we want to bring those into the learning process. So unpaired, unsynchronized data. So in a nutshell, the approach that we developed has a couple important features. We developed a transformer-based encoder that has a loss that says do good temporal alignment. So what's the least cost way we can put these two frame sequences into alignment? That's based on dynamic time warping. But the two elements that we bring into this, here is like the exo stream and the ego stream, learning an encoder for all these frames. We have an object-centric encoder. So we found that, as you might expect, it's non-trivial to decide what matches between these two very different frames, but the thing that does persist is the hand-object interaction. And so what we do is find regions of interest based on active object, hand-object interaction detection, and then expose those to the encoder explicitly. And secondly, we have a contrastive regularizer. This is a self-supervised idea that says if we have an ego sequence and an exo sequence, then we want the cost of aligning those two, given that they're from the same action, to be less than what we would get if we reversed the frames of that ego view. So here they're just mapped back down in the opposite order, and then try to align that to the exo view. So we say it has to be smaller cost. So alignment we should be able to find a better alignment from the first two than we would find from the second two. So those are the insights we have. And now we took it to 4 different pairings of data sets. So each chunk here, 1, 2, 3, 4, is a different action, like breaking and exploring, coming from some public data sets that we, in certain cases on the bottom row, kind of put together ad hoc. So like epic video on the bottom left, paired with some third-person data from HMDB, another video data set from the exo view on the right, both for pouring actions. So 4 different data sets, each of them now ego-exo, but we treat them as unpaired. And in fact, the bottom row, these are very explicitly unpaired because we just pulled them together. And that means that between the ego and exo views, different people, different environments. And then for evaluation purposes only, we provide action phase labels, giving those fine-grained milestones of the activity. So what the results in the paper show, which showing you 4 data sets, A, B, C, D, and then kind of our models results, just to convey all the evaluation we've done to look at the variety of data sets and tasks. Really, the tasks are focused on this fine-grained action phase classification. And we see very consistent strength of this embedding compared to, importantly, what we could get with existing models that require paired data, as well as what we could get with existing alignment-based video representation. Most visually, what we can see then is what we can do for alignment. So here's 2 source videos, ego and exo, different actors, but in a kitchen breaking an egg. And you can see that they're both breaking an egg, but those are not in alignment, right? 2 different captures. Once we take the encoding that I just described and then do some simple nearest neighbor matching, we can put these into temporal alignment. So think of taking every frame from the ego view and then finding its nearest neighbor in our learned feature space in the exo view, and now playing those back side by side. And this is what we'll get. So watch this short clip. This is our output synchronized. You can notice that the one on the right kind of had to pause in order to stay lined up with the one on the left. So that now even the moment of breaking the egg was about at the same time point, as well as the completion of the action. So subtle things, but now coming out of this improved learned embedding from the ego-exo alignment. And in fact, we can achieve the kind of embedding visualizations like I motivated earlier, where instead of just, seeing nothing but how different ego and exo are, which is what this kind of original embedding does, we're seeing how they align in a viewpoint invariant way and keeping track of their action phase. Okay, and just another second example, just the same kind. All right, so in the remainder then, I wanted to finish with this example of looking at video from the instructional point of view. So we're very motivated by, thinking about how you could translate skill from person to person, if not person to robot. And here, when we talk about person to person, what a great resource is a how-to video. And here's an amazing video data set that looks just at this kind of content, how to 100 million, thousands of different kind of tasks. And this video has with it also language narrations. These are very in the wild because it's transcribed speech recognition by speech recognition to tell you in text what the person giving the how-to was saying at any given moment. So it's noisy, but it's very rich because you're hearing these instructions and also witnessing the visual instruction at the same time. But here's the thing, so because of that noise, people say all kinds of things that aren't about what they're doing. And what we wanted to know is, can we detect the difference? So what we call this problem is visual narration detection. So we say a visual narration is one where what is being spoken is exactly what is being shown. So on the left, yes, that is one because the person said add a half cup of diced carrot and the video shows someone adding a half cup of diced carrot. Now these others we'd say are negatives. They are not visual narrations because they're describing things, some just color commentary like, look at this, it's perfect. Some are actually topically relevant, but they're not showing what's shown. They're not saying what's shown. Okay, so being able to tell the difference is very appealing, and to do it in a task agnostic way, this would allow us to take new videos in and find the hot spots of where there's really good instructional aspects and make a video summary, or in the case of robot learning, to be able to give the robot the right parts to pay attention to if you're trying to imitate a human actor. So our method in a snapshot is this. We will find alignment between a small set of key step labels on some videos. Here's a key step label, take out the wiper, it's expressed in words. And then look at those narrations and do some language-based matching to find out when the narrations agree with a known key step label. And so in some cases that will be yes, it does agree, and that would make a positive, and others it won't. So lift the wiper blade, take out the wiper is a yes. See, this is off, it's so easy, take out the wiper, that's a no. And so we're just bootstrapping up from weakly labeled data, examples of visual narrations, and then learning a cross-modal embedding that uses that supervision to put close together the right visuals with the right narration. Furthermore, we bootstrap further from the full data set of how to 100 million by pseudo-labeling it and augmenting our training. So what do these look like? Here are things that the model, through this process, we discover as visual narrations. So cases where the person says what they're actually doing. So remove the seat, fully tighten the screws, add the strawberries to the blender. Now we flip the pancake. Okay, these are all very much aligned, and these are positives for visual narrations. And then here's some negatives. Hello, my name is Mike. Oh man, it smells so great. But some of these you would detect from language alone. But as I'll show you in a second, that's not enough in the numbers, because a lot of things will be described that are topically relevant and maybe even could have been illustrated, but the person didn't do in that video. And so we're able to start to learn the difference. And our improvements here on the right, this is accuracy on a manually labeled test set to say how well we could do compared to just looking at a language model, checking whether objects mentioned are in the video, and other temporal alignment based approaches to this test that we built as baselines. Okay, so finally, summaries then can come from this model. So just taking the how-to video and then finding those clips where there are visual narrations, we can provide a summary. So selecting the subset that's shown here for how to make short rib pasta video gives you just those steps that are demonstratable and described. Or similar here, where these are just the ones that were chosen as visual narrations. And they nicely start to show you this play-by-play of what you actually need to do to complete the task. As opposed to all the ones we dropped, where she may have been talking about things that have to do with the actions, but they aren't the ones she's showing right there, like adding flour or making it less spicy. These are the ones that get weeded out. All right, so I'm going to close the talk here. I've shown you ways in which we're working with first-person video and it's generally an instructional video too, to learn new representations that account for the semantics, the goals, and view invariance, as well as starting towards applications where we use our understanding of human action and descriptions to do things like video summarization. Highlighting our first authors here, Ashutosh and Sherry, and be really glad to have any comments or questions. Thanks.
This is maybe getting into technical weeds and I should just go to the poster session, but there's the aggregation step. So when you're doing the feature alignment, I guess I'm curious, one, like what is the actual aggregation? But then when you showed the T-SNE plot, you showed that the original features and the child features and parent features were getting embedded together. Is that the aggregated child features or was it the individual sort of separated features?
Yeah, it was the individual child features and the summary features kind of, because it's all a single language embedding for that comes out of it. So that's what you're looking at with the T-SNE. And then the aggregation, we did explore a couple of variants. One just average pooling and the other a transformer based aggregation, which was stronger. Yeah, Rob.
Maybe I'll just shout out. So in the work that you were talking of this Go EXO alignment, you mentioned that you used objects. Were those specific object detectors? And if so, were they like, did the object detectors have sort of the same labels for the two views? So that it's
Right. No, it's not specific and it's not, there's no taxonomy alignment that came. It's off the shelf hand object interaction detection model that we use. So it's defined hands and active objects, meaning those that are being currently used. So I'm thinking, as far as constraints on, we did no extra work to line these up.
But so you segment those out and you get features from those.
Yeah.
That's
Yeah, that's right.
Thanks.
Yes.
So at the end, what so first we do label and then use the filter now, or you just the label. I didn't get that.
Yeah. So the thing we're pseudo labeling for is visual narration, like yes or no. And so if we have the original model, which is this embedding, where you can now take a text blurb and a visual video clip and see if they're close or far, then we can do the same thing on this unlabeled how to 100 million from its spoken ASR text and each video clip. And then this would allow us to say, okay, let's take all the most confident close pairs as plausible visual narration examples, and the others as negatives. And now you have, million, whatever it is, thousands, hundreds of thousands more samples with which to kind of augment the training and review. So think of like broadening the training set that way.
And this training was not in the table.
Could you say again?
The training was not in the table for the people.
No, this one is trained then. So starting the kind of seed set that does have labels is from Coin and Crosstest. These are two other data sets. Start with that and then go to how to 100 million, but no, we go 40 in this case. Yeah.
Thank you very much for your talk. We'll continue with the panel session. So. Please come from. So. Here.
And to continue the panel session. I am Mara Halawa, I will moderate this session today. Be joining me in welcoming our great panelists. So, Dini Bari, Abi Stariano, Elke Demir, Judy Hoffman, Christine Grauman, and Anjan Shire. So, thank you very much for joining us today. And I'll start with some questions we received from our forum, and then we will open the room to receive some questions from the audience. So our first question today is, where do you see computer vision will have the next big impact?
I'll jump in with sort of my own perspective. I work a lot with plant biologists, and I think there's sort of huge opportunity for an emphasis on vision for science. One of my favorite researchers, Sarah Berry, was giving a talk at Earth Vision yesterday, and she talked about this issue that like we have all of these really cool models that everybody's really excited about, and they kind of don't actually work in sort of real world domains. And that's not, it's a little flippant. They certainly do in lots of applications. But I think, when I look at plant biology applications, it often is the case that if we try and take something sort of cool and off the shelf, it doesn't work. And there's a lot of work that has to be done. And there's a lot of need and desire in not just plant biology, but all sorts of science to take these things that we think in vision are really cool and exciting and hot and getting advertised all over the place and actually do some real sort of hard science in some ways. I think that's one opportunity.
Okay, I will jump. So I know that recently, like both the hi, hello, better voice. Thank you. Computer vision was stuck a little bit in the 2D domain for detection, recognition, classification, segmentation, like all these traditional tasks. And nowadays, very fortunately, we are going actually the synthesis tasks like generative AI and all the advancements that we see. But I really think that the advancements in that domain in multimodalities, especially in 3D, for 3D content generation, for digital humans, for digital worlds, for carrying us beyond the current 2D digital barriers through 3D, not only by representation, not only by just meshes, point clouds, whatever, but also with the interactions, how do we represent ourselves and how do we feel in 3D, how do we touch in 3D, how do we navigate in 3D, etc. So I think the computer vision applications carrying us to multimodalities and multiple dimensions is where we should be going and hopefully having a huge impact.
Maybe I'll follow up on that a bit because I completely agree with the first two and especially the multimodality. But one thing that's interesting to consider is the word vision, right? Vision is very vision focused about what we sense via the eyes. But I also see that a lot of people in the vision community are also moving to other modalities, which are not just visual, I think audio is making a lot of progress. And in addition to that, there's also potentially, touch sensors as well. And so it's interesting to consider going beyond the traditional images to these other senses. I don't know how much data we have there, but that will be a very interesting direction.
Anyone want to add something?
Can you maybe add a little bit that, and maybe to your point, since you were emphasizing on vision, that I think there is a chance that going forward, this sort of vision-centric way of thinking about things may not necessarily be how we approach it, like maybe similar to LLMs, where you kind of prompt the system to do all sorts of things, and you give it a few examples, and it does things that are fairly useful. I think vision tasks becoming a part of that ecosystem may not be that far out in the future, where you upload an image and you say, oh, I want all the objects segmented out or detected, or even interacting with generation tasks, that this is how I want the image to be edited. So people who don't have a sense for what all the vision tasks are and what the taxonomy of data sets and tasks and metrics and all of that is, just being able to interact with things and extract out any understanding that they care about, or generate or edit in very natural ways, I think is not something that we are very immediately seeing right now, but feels like it's probably not very far out, given that we're seeing things with LLMs and multimodality in particular, with like GPT-4 already starting to have a little bit of this in terms of ingesting visual content, right? It doesn't produce visual content much. Yeah.
So the second question is, what is something you would have done differently in your PhD days?
I can give one. So I think work-life balance. I feel like I've gotten better at it, even though my life has become more complex. So now when I'm meeting family, children, and just, amount of work or responsibilities much higher now, and I have a much better work-life balance. And so then when I look back at my days as a graduate, and like it would have been real simple to have a really good balance, but I don't feel like I always did. By choice, I would think I was working a whole lot because I enjoyed it, but that doesn't mean that's the only thing you need to do. So I feel like that's something in hindsight I could have done better.
We are waiting to jump. Who's jumping? So maybe very complimentary. I think a part of that I should have done much better is actually collaboration, because when it's parallel to what you just said. We tend to work a lot and overdo and not have work-life balance because we are not sharing the work, because we are not collaborating maybe. And in my case, it was the case. So I don't know whether you have played the game. There's a game where a character says collaboration, collaboration, collaboration. So it always echoes in my mind. So I think if I can go back, I would not be the only person doing everything about the project and implementing and writing and experimenting and everything. Trying to collaborate more with other labs, with other universities, with other people in my lab, etc. And I don't know whether that was my choice or that was imposed on me. I don't know, but something that if I had known, I would have done better collaboration during my PhD. And because I learned that, now I'm collaborating with everyone.
Yeah, so I like both of those examples that were given. I think the really good things to work on during your PhD, but more broadly, I think during your PhD is establishing the framework for the way in which you're going to work, whether that means collaboration or whether that means how you're going to balance your work. You need to establish different time management tools during this time. They'll help you a lot. You also need to start getting comfortable letting people down, saying no to things. At first, it's very exciting. You say yes to everything because maybe you only get asked a couple of things a year, but you'll get asked more and more things in the future. And I think something that I wish I would have known more about in my PhD is I had this sense that whatever I was asked to do, I felt like I had to say yes because I'll never be asked again. So just kind of having confidence in yourself that this is only the beginning. You will be asked to do more things, and so you need to be judicious with how you decide to spend your time. This is not something that I would change, but I don't know where this came from or when I started doing it, but I heard advice from somebody to come up with a yearly budget for certain things like service obligations or various different things you want to do. It can help you to prioritize what you want to say yes to in a year, and also give you a very firm rule. If you've already reached your quota for the year, you should say no to everything.
maybe I'll say a few words about myself in the sense that when I was a PhD student, I was a bit clueless, probably because I didn't really interact with other people very much, like talk with them. I didn't really know what to say to people. And it was also very hard to approach people. And I always felt like, oh, I'm uncomfortable, right? And at some point I realized it doesn't matter, you just don't worry about asking a stupid question or just talk to people. And the more you talk to people, the more comfortable you are. And it's practice just like everything else. And so, so don't be intimidated, just say whatever. And I also find, this is something I do find, that I actually did my PhD in the NLP group with the NLP community. They're all very nice people, but I also find the vision community to be extremely welcome. So everybody's super nice, and they, nobody's gonna say that you don't belong here.
I've got one that I think isn't specific to the PhD. So it's for anyone, whatever stage you're at, but don't compare yourself. I think I'm horrible about this day. So some of you may know me from doing social media chair stuff, which means that I am looking at the CVPR Twitter and the ICCV Twitter and the WACV Twitter like every day. And I see like everybody's self-promotion of like their amazing work, and I'm retweeting it and just feeling terrible about myself. And like when I got invited to be on this panel, I looked at these other amazing women. I was like, what the heck am I doing here? And it's toxic. So don't do that. Everybody's circumstances are different. Their priorities are different. What they're excited about is different. And you should find what you're excited about, and don't compare yourself to other people, because there's nothing positive that comes from that at all. So don't do that. And I should take my own advice.
It is absolutely fine if you are not tweeting that your lab published 8 CVPR papers in one conference and 12 ICCV papers in the same year. It is okay if you are not in that lab or if you are not managing that lab.
So the third question is, maybe I continue on to this, like how do you respond, in general, how do you prioritize and split time between what's the research project, personal life, hobbies? So yeah. Maybe this is different also between when you were a PhD student and now you're neither of them.
I mean, this is a really challenging question that I think is something that I have to work on constantly. I try not to be too hard on myself. There are certain times, maybe near a deadline, where you have to work a lot. And what I just try to remind myself of is that when there's not a deadline, maybe I just need to take a Wednesday off. Sometimes that happens, like you need to balance out on, a long-term horizon rather than, I don't usually worry as much about having work-life balance on a day-to-day basis. Now, I don't have kids, so it's a different situation. If I did, then of course you would need to carve out time on a daily basis as well. But whatever life situation you're in, I think work-life balance is about understanding that you're a holistic person. You need rest, you need social interaction, you need to enjoy other aspects of your life. And you need to be able to do all of that, even if your overwhelming goal is productivity, because it will suffer if you don't do those other things.
Maybe I'll say a few words about that. I personally, I don't think I have very good work-life balance, partially because my partner is also like in the same area, and that makes it hard. But I think everybody, I think, is a little bit different, and it's about what you want, in the sense that if you want to, so if you are maybe a bit more ambitious, or you want to like spend a lot of time, or you want to achieve certain things, you may have to give up a little bit of your more life balance and focus a bit more on work. But then, on the other hand, if you want to have a family and you want to enjoy yourself, you shouldn't feel like pressured to like compete with everybody. And then you should try to allocate time and just be conscious of where you're spending your time and why. And I think the worst thing is for you to think that you want to achieve something, but just spend all your time in front of a computer,
but not actually efficiently using that time in the sense that you're stuck, you're not getting enough rest, you feel pressured into it, and you just, you're not doing this extra, other going outside, having exercise and maintaining yourself, and you just feel pressured to be there. You're not, you make your decision. So decide what you value and allocate, proportion your time accordingly.
So I think I tend to not think about work versus life in those terms. I think I tend to think about life as a portfolio overall. And I think it's because even within work and what we normally call life, there are things that you prioritize, right? Like on work, like across multiple research projects, which one can I be doing all of them? You need to prioritize how much time I'm spending in each one. If you're sort of managing people, you're figuring out how much time do I get to spend on research versus on managing people, on service roles, all sorts of things. And then even within life, right? Like how much time do I have to watch TV shows or like hang out with friends or craft projects or other hobbies that you might have. So I feel like this whole notion of prioritizing and figuring out how much time you want to spend where tends to go across. And so for me, it doesn't tend to show up as life versus work. It's just like across all of these things that I'm trying to figure it out. And so my principle, and it's not very conscious, but I think the way I tend to function is just whatever I'm excited about right now is the thing that I'm going to be spending a lot of energy on. So to Julie's point, that if there is a deadline coming up, that's what's on my mind. It would be very, very artificial for me to insist that no, I'm going to watch 2 hours of TV shows no matter what, right? The day before the deadline, like that's just not going, it's just not, I'm not going to enjoy it, right? I'll be forcing myself to do it and there's no point to it. And then on Wednesdays, like if there is not much happening, this last week on Friday, because this is a long weekend in certain institutions, Friday was particularly slow. And so like I was watching Netflix in the afternoon, right? Where like that's just, yeah, like who does that, right? On a working day in the middle of the day kind of things. I think that's just based on what's going on, what is it that I'm excited about. I tend to naturally allocate time across what we traditionally call work and life. And separately, I have this whole mechanism with how I manage time, and I've written about it. And if anyone's curious, I'm happy to share that with you. And that I think also helps quite a bit. Like TV shows explicitly just are on my calendar, just like a meeting is. And then I'm not prioritizing, right? Like I've already decided that's where I'm spending my time, and it's not like actively I need to keep fighting one or the other to do that. And I think that has made a big difference in terms of just mentally being peaceful across whatever it is that I'm trying to do.
I remember there is a color-coded calendar, so that is a very useful time management tip. If you want, like just search for it, you will find it, I hope. I just want to say that time may be linear, but productivity is not linear. So very little people know that like I have a double life. So normally I'm doing research, like I'm like managing all these projects, right? But at night I'm actually a dancer. So I social dance, I teach, I choreograph, I used to have my own teams, etc. So I found that like actually earlier in doing my PhD that if I go dance, just like practice 1 hour, then I am so much more efficient when I'm going back to my research and like coding and writing the paper, etc. It's like a really different pause. And when you have that pause and when you switch your brain and then come back to hopefully that it may be a workout, it may be dancing, it may be, I don't know, social activities, etc. But like when you do that context switch, your productivity, my productivity, and hopefully some of ours increases so much than I expected. So giving 1 hour break for whatever else makes your next 2 hours of research actually like maybe more than 2 hours, maybe 4 hours, etc. But if you are not giving that 1 hour break, then it will be even less. So don't forget that, like, when you are planning for things, productivity may not be linear. Just that's my motto.
I think that's super healthy, this idea that like take time for yourself because that will actually help with your work. I do want to throw out that there are some things that you have to take time for yourself that do not have that impact. So I'm a young mom, I've got 2 kids, I have a 6-year-old and a 1-year-old. And I wish that people had made clear to me the like extent to which my brain would just turn to mush because of kids. And being a mom is amazing, and it has had real impacts on my career, and that's just the reality of it. So family time is wonderful and can help with productivity. Parenting time sometimes does take away from that, and it's hard. I come to this strictly with an academic perspective. So I've had came out of my PhD and got a faculty job. And I think that one of the things I didn't understand, and people tell you this, they're like, your first year as faculty is just going to be sort of shocking. This idea of all the things that you have to balance that you don't realize when you're a graduate student that your like PI is doing. And I forget, Judy, if it was you mentioned this, like sort of your budget for the year of like, you can only say yes to so many things. And there's so many things as faculty that you kind of do have to say yes to. There are service obligations and there are teaching obligations. And when you're a grad student, you don't realize how that's going to be, and nobody can prepare you for it for that like first year of the academic job. But I think it's really, that makes it even more important to set up this budget. And if anyone hasn't read Davy's blog on putting everything on your calendar, you should, because you'll very quickly realize that you can't keep saying yes to everything. Literally aren't 2 hours for it.
Okay, so now the question is more researchy. So what is the value of transfer learning, domain adaptation, or continual learning in the age of foundation models and data-oriented engineering?
I feel like that might have been tagged. I want to expand that question and say it's not just transfer learning or domain adaptation or continual learning. It's also recognition. It's also what are we doing with, you know, how are we going to use vision models as a tool to solve other tasks? And I think that that's something that harks back to the very first question of this panel, which is basically what's next in computer vision. So if we have access to a big model, well, how are we going to use it? So we got one example of a case in broader science where they want to be able to use a vision system and it's not working. But hopefully you'll be able to use that big model in some ways. Maybe the way in which you want to use it is maybe the information that's needed is there, but it's just obscured by all the other stuff that it was trained with. So maybe you need to develop fast specialization tools. Or maybe you need something like Aura from NLP, where you can do fast fine tuning of just a small amount of parameter space on a little bit of data. So I can see that that would have big impact in a lot of application areas if you were able to really leverage these big models, maybe only a portion of them, so that you don't have to have mega GPUs in order to process them, because that's not something that all scientists have. That's not something that all practitioners have. So trying to think about if we were in a world where you had these big models, we're already starting to get it, but you have these big models, they can solve a lot of tasks. It seems really compelling. How do we basically make it such that they can be used in all kinds of different circumstances under a variety of constraints?
Actually, now the one who said sent this question asked us to ask you. So, okay, the question is right now, how do you respond to people who feel that women are getting unfair advantage currently to the affirmative action?
Well, counted for all the benefits and advantages that the non-woman had during all the years prior to now, so that this is just a little bit.
Or actually, also, I like sometimes I don't see there is an affirmative action. Like some people say there is affirmative action, but we don't see it. Do you feel there is affirmative action? I think more supporting women.
How many of you have ever been told by a colleague or a peer that you got something because you're a woman? So regardless of whether it's happening, it's being communicated to us. And I think this is one of the most devastating and detrimental parts, that you start to doubt yourself and feel like you got something only because of some aspect of yourself that has nothing to do with your work. And I would say, just try to let that go. Here's the thing. Even if that was true, oh well, people get advantages for all kinds of different reasons. Just take advantage of it. Move on. Make the most out of the opportunities that you're given. Very likely. But very likely, in many of the cases, that's not the underlying reason. They're not going to give this opportunity to just anybody because you're a woman. They're giving it to you because of who you are as an overall person and the things that you've accomplished. So just be confident in that aspect. It's really, really hard, especially when you have peers or even more senior colleagues that will say things to you. I have been told more times than I can count or hinted at that the reason I got something is because I'm a woman, but just forge on. Take the opportunities as they come.
I was actually chatting with some colleagues last night about sort of making our community safer for women. I think that's sort of an interesting thing that I have felt very safe in this community, but I don't think that's a ubiquitous experience. And I look at other communities and think they do a better job of this. So like the computational geometry community, has like the Safe TOC sort of leader group that makes sure that all of their conferences have ombudsmen and like mechanisms for people, not just women, to come forward with sort of issues of safety and concerns and how they've been treated. And I think that's something I'd like to see our community do a better job about and sort of make things safer for people in general, or sort of freer for them to come forward with issues. The specific topic of conversation was like, we sort of hear things about like underground sort of network communication about like advisors who are not safe or might be abusive to students, and this shouldn't be an underground thing that you like have to know the right people to find out how to be safe. So I would like to see us do better on that going forward.
So now we can open the room for some questions. We can take 1 or 2 questions.
I come from the science community before moving towards development. And I've always been one of the few women in my field. I have been barely actually, when I first started, I barely met any girls in the field. That's where I come from. When I moved into science and all that kind of thing, I started to notice that there's a lot more women around, which is really exciting and all that. But like you said, whenever you said something about the next generation being science, AI is science, assisted AI, how can, in your opinion, how can we actually motivate women into venturing towards, computational sciences, things like in that direction, especially coming in from something that might not be heavily computational. I was lucky that I was doing geophysics, really computational anyways, for science. So it wasn't like a huge shift, but for people that might be maybe doing biology, I know they've done biomedicine, but like still, it's not accessible. But the research might be, we'll need it. So how can we actually do that? How can we motivate women? Because I have also noticed this in my field. Not a lot of women come in initially into the field, but then never even learning how to. So from your experience, what would be the best kind of thing?
Yeah, I think one thing I've noticed, so I think it starts early. So I think generally what you're talking about is kind of broadening participation in a field, or really igniting interest in a field that someone might not accidentally encounter or might have preconceived notions about what it really entails, like whether it's computer science, computer vision, or any other subject. So what I've seen at University of Texas, where I'm faculty, is or what I think is a really exciting approach is not unique to UT, but just starting early and dispelling the myth of what the field is about. And like this example of connection to science is such a great one. Science, economics, fashion, language, everything. And so concretely what that can mean is programs for K-12 for exposure to very accessible CS-based talks, vision, whatever it is, that's geared towards children to see what the scope of the area is, or at the undergraduate level, kind of we used to have, started as classes like computer fluency. Maybe the name doesn't make sense now, but it was to like what is computer science for someone who's not touched it yet, you know, and so it wouldn't have to be a heavy programming class, but something just to expose what the ideas are or what computation could mean. And so I think these things are really valuable, like a lot of work and a lot of resources to do them, but something that we can try to control. And I mean, measurably has impact for like broadening that pipeline early, not just women, but like students who weren't going to go that way if they didn't get this like glimpse.
Okay, thank you very much. So I guess we are getting to the end of this session. I would like to thank all the panelists for this great discussion. And I really also would like to thank all the audience who makes this event really successful. Thank you very much. Now we are getting to the last part, which is the poster session. So we will all move to the poster area, and our poster will be between numbers 149 and 183. So you can put your posters, and you will have around an hour for the posters, and then see you in the mentoring dinner for our great keynote speaker, Elke Demir and Abi Stagliano. And yeah, thank you very much.
Making my talk for tonight that people will be eating, like, give it, and I have things I talk about it. They're not always appetizing. No, I should shift that.
I guess they left. Okay, so
I think they had to go for the poster session, like in-person poster session. So everyone else is present. I've sent the link to Topia. You can visit the virtual poster sessions at Topia. I think we have some people already. Yeah, I think we'll be closing this. I hope that everyone virtually moves to Topia. Thank you very much for attending.
thank you. Hope everyone got link. Yeah.
I'll send it again.
Yeah, just in case. I guess they are leaving, so maybe they got it.
Okay, cool. Should I end them? I'll end the meeting then.
Okay.